some. So
Hi, Esther.
Hey, John.
Do you want me to play the video?
I think I can play it.
Okay,
yeah, I tested it. Yeah.
So I went to another Zoom link, and there are people there.
Uh-oh.
So maybe something is wrong.
Uh-oh.
There are
all right.
10 people.
Tracy?
Yeah, this is Tracy. So what's going on?
So I went to the Zoom link you shared with us last Friday.
That must be Elizabeth. Sorry.
Oh, yeah.
Yeah, just stepping in. So you went to a link she sent Friday, right?
Yeah, and there are people there. I think I can go there and tell them.
Let me send her a message.
And maybe, Jean, if you could go there and give them the correct link and password. Do you have that?
Yeah, like in the chat, maybe.
Yeah, let me try to do that.
Okay, so we'll wait a few more minutes, maybe.
Yeah.
Okay, okay.
When you come back, we know it's okay.
Okay.
Yeah, Sarah in the chat said she got 2 links the other day.
Yeah, one for today, one for tomorrow. Different links, right?
As far as I know, I don't want to give people wrong information, but I thought it was just
Yeah, and I'm sorry because I'm not
1 link, but
I'm not the organizer, but I'm sending Elizabeth a message.
yeah.
So we can start 5 minutes late. It won't matter.
Yeah, we'll just, that's fine. We want to make sure to give everyone their time, but we'll just shift.
You need to make sure Axel doesn't sleep while giving his talk, though.
Yeah,
that's true.
Should we have a little sing-along while we're waiting? Keep Axel awake.
Yeah. You can all sing something. How about that?
Actually, I'm a night person, so I could do midnight. It's when these 2 or 3 a.m. starts that start to get to me.
No, I have some energy. He has nuts, so it will be fine. Did anybody ever calculate how much CO2 we saved last year, the climate community, from not traveling?
Oh, yeah, there is a paper by Corinne Leukere in Nature Geoscience or Nature Climate Change, one of the two. They looked at it. It's about 5%. Not much.
Sorry, I'm talking about the climate community, Thomas.
Oh, not the global community. Okay.
Oh, if it's 5% just on us, it would be terrible.
Okay. The climate community. I don't know.
I've been looking at it, actually. It's interesting that in terms of the travel, business travel, there was a recent study by Hamburg International Airport. Business travel apparently is only 5 to 10% of the total worldwide travel. And that's total business. It's including for business purposes. So the carbon emissions, the travel emission related planes and all that stuff is only 2% of the total emissions. So when you look at it, 5% of the 2%, and then I actually calculated also the CO2 emissions due to computer simulations. So if you run our model, high-top version of the model for 17 years, it's equivalent to 1 round trip person travel from Denver to Europe. Huge.
Yeah. What about all the Zoom meetings?
Well, that's another thing. That's
yeah.
And the numbers are going up, so maybe people are starting Was anyone that's just joined on the wrong Zoom call? Let us know.
That Zoom call is for the Hemisphere Working Group meeting.
Okay.
Ah,
And I let
Okay.
people know that.
oh, okay.
So there are two meetings going on right now. One is atmosphere, so people
Yeah.
may be registered to both and then going to the wrong place. So it's not the.
Okay, should we get started here? You think
I'll
we
give
should
them
wait
a-
a little bit longer?
Yeah, I'd give them another minute or two, Esther. So it looks like we're up to
We're up to
30, so we're getting there.
Okay, let me share this welcome slide while we're waiting.
I think you can probably welcome people, Esther. That'll give them
Yeah,
a couple
I
more
just-
minutes.
We're just supposed to put this slide up to welcome everyone. Yeah, good day, everyone. I want to welcome you to the winter meeting of the CESM Paleoclimate Working Group. We have a great set of talks lined up for you over the next 2 days. We're also going to have a discussion at the end of or following Tuesday's talks for brainstorming how we can best move forward in this working group. And then following that, we're hosting an informal chat for anyone who'd like to stick around and talk about their work informally or continue the discussion. So to get started today, I'm pleased to begin our session with a keynote presentation by Axel Timmerman, Director and Distinguished Professor of the IBS Center for Climate Physics, Busan National University, Korea. He became director in 2017, moving from the University of Hawaii, where he was a full professor in physical oceanography. Axel served as lead author on the Information from Paleoclimate Archives chapter of the Fifth Assessment Report of the IPCC. He's a fellow of the American Geophysical Union and has received the Milankovitch Medal in 2017 from the European Geosciences Union. Today, he's speaking on a 2 million year transient paleoclimate simulation of the CESM. So let me stop my share. And you can take it over, Axel.
Okay. Thanks a lot, Esther. And also, thank you, Betty, for inviting me to this meeting. It's a real pleasure to see so many familiar names on the Zoom call. So I'll talk about our latest simulation, 2 million years transient paleoclimate with the CSM 1.2.2. And I would like to acknowledge in particular my colleagues at the center, Kyung-Suk Yoon and Elke Zeller, Daniel Lemon, and from the PIC Andrzej Ganopolski and Matteo Willeit, who provided some of the forcings for these model simulations from a more intermediate complexity simulation that they conducted previously. So now I need to move forward. How do I do that? Okay. So one of the main motivations is for us also to understand the effect of past climate change on human evolution. So I'm always talking about this idea to come up with a Milankovitch theory for human evolution. That's still a dream. We are far away from that, but we are trying to use these simulations to address questions that are relevant for understanding the variability in vegetation, megafauna, and also hominins. And one of the other goals is also to understand how a genetic and cultural diversity formed and whether climate actually played an important role there. I would like to give just a brief history of our paleo modeling adventure. It started in 2004 with my PhD student Flavio Justino, who ran a fully coupled LGM run with the Lgm Earth System model. And afterwards, Uta Krebs picked up that model version and conducted several water hosing runs with the LGM setup. Then Oliver, Ellis, and Tim joined the team then at the University of Hawaii, where he conducted the first transient 21K simulation 2007 with this model setup. In 2008, we had a 130,000 year transient simulation, which included ice sheet forcing from Ayako Abe-Ushi's ice sheet model simulation. Then Laurie Mienviel is a PhD student at the University of Hawaii. She used the same model for transient MIS3 experiments, where she essentially simulated each of the individual Dansgaard-Oeschger events by adjusting freshwater forcings. Then Malte Heinemann coupled the ice sheet model from Ayako to the Lgm model, and we conducted also 80,000 year transient experiments going through an almost entire glacial interglacial cycle. The issue there was the glacial inception was a bit iffy, but the termination was relatively easy to simulate. Tobias then played around with these longer term experiments, and some of the philosophy that we developed in 2016 is also adopted in our experiments here. You will see that later on. So we conducted a 784,000 year simulation with Lgm still that used the ice sheet forcing from Andrei Ganopolsky's Climber simulations and CO2 forcing from Epica. Then Dipayan Chaudhary, when he joined our center here in South Korea, he coupled the Penn State ice sheet model in both hemispheres, Northern Hemisphere and Southern Hemisphere, to Lgm. That works now quite nicely. We can simulate almost an entire glacial interglacial cycle. And then Kyung-Suk Yoon, an associate researcher in our center, she then adopted some of these earlier transient simulation techniques to conduct a 2 million year experiment, which I'm going to talk about. She also coupled the CESM to the Penn State ice sheet model in both hemispheres, including Antarctica, Eurasian ice sheet, and we are also conducting transient experiments right now. All the data from these previous runs that we conducted are available online, either via an LAS server or opened up. So lots of paleoclimate interested scientists have used these data sets. One part is hosted on the APDRC, Asia Pacific Data Research Center site, and some of it is hosted on our current climate data web server. I will talk about it later on. Okay, let's talk about this 2 million year experiment. First of all, we need the forcings, greenhouse gas forcing. The first 784,000 years are from Epica, and the period before is taken from this experiment that Matteo Willeit and Andrei Ganopolsky and others conducted using the good old Climber workhorse, which is much more simplified than the model that we're using. And we also use the ice sheet forcing that they have generated. This is a fully coupled intermediate complexity climate ice sheet carbon cycle model. And from these experiments, which ran for 3 million years, we took the greenhouse gas forcings and the ice sheet forcing. And the orbital forcing is, of course, the good old Berger. The model version that we have adopted here is CSM 1.2.2, T31 resolution, because we want to run a lot of model years. And the ocean has GX3V5, so that's about also 3.6 degree and 25 levels in the ocean. The model is running parallel on 16 Skylake nodes on our supercomputer, and we can get about 300 years per day on 16 nodes. We have more than 400 nodes available, so we can run a lot of segments actually in parallel, and you will see that later on the kind of technique that we are applying. Okay, so the forcing gets updated every 100 years, and we use in the CSM the orbital acceleration technique, but we use a relatively low acceleration factor of 5, which means that the orbital history of 2 million years gets squished into 400,000 model years. But even 400,000 model years is a lot of data that is being produced. About 500 terabyte CSM standard output has been saved and will be made available later on. We did not play with the land sea mask, so that's similar to the experiments we did previously with Lgm. We use the Lgm bathymetry for the entire period. That's an approximation. Given the fact that most of the time, 80% of the time, we were in glacial periods, I think it's a reasonable assumption. And what we have not included is the sea level lapse rate part, which I think, I'm not quite sure whether it's included in all of the PMIP runs. Even the fact that if your sea level drops by 120 meters, that is already 0.6 degree on your lapse rate. So that is, I should also mention the greenhouse gas forcing is slightly amplified. So that's a method to compensate for the relatively weak climate sensitivity of CSM1 2.2. We were not happy with the climate sensitivity relative to the Paleo estimates. So rather than changing the cloud parameterizations and all the complicated knobs in the model, we just intensified the forcing, and that is something also of an approximation here that can be discussed later on. All right, so 2 million years, even on our machine, if we just ran it sequentially, would take about 5 years. That's too much. So we used 20 parallel experiments. Each of the experiments starts in an interglacial and runs through a glacial into the next interglacial period. And then when we have the overlap between the last interglacial one and the next one that is starting, we can essentially see how well does this match, or do we need to interpolate. So currently what I'm showing here are the interpolated ones, where the run that is finishing essentially slides into the next new simulation. And that technique works also reasonably well. Even for the ocean overturning circulation, we have tested this, it works quite well. Yeah, that experimental design has been discussed earlier on. So running 20 experiments in parallel, we only ran essentially the simulations for 2 months real time. But I just calculated the CO2 that we burned. So that was about 200 tons of CO2. So that's something to keep in mind. All right, so just to give you an idea, this has nothing to do with the simulation right now, but just to look at the orbital forcing for the last 2 million years. Looking at the dominant EOFs, so here we see the dominant EOF of annual mean insolation, the typical obliquity pattern with a sign change at about 40 degrees. And the dominant principal component is obliquity cycle. And you also see the nice long-term amplitude modulation that people have looked at before. It's quite nice, and it has also an effect on the climate system. Then, of course, the annual mean insolation is not large on the eccentricity timescale, but again, I would like to highlight here, we have the 100,000-year cycles, but, and I will talk about it later on, we also have nicely the eccentricity on the 400,000-year timescale, which is very often kind of swept under the rug, but I think it's really, really important orbital forcing that I wanted to highlight here. Well, we'll come back to that later on. Okay, how well does the model compare with Paleo proxy data? And there are a few reconstructions of past global mean surface temperature. I'm just showing here one that we made using SSTs in 2016 in green. And in blue, you can see the simulation, the 2 million year simulation. And overall, the amplitude matches quite nicely between the reconstruction and our simulation. And it also matches the original Willite simulation. Well, that's probably just because we use their ice sheet and CO2 forcing, so it's not too surprising. But there are two things that I wanted to point out, in particular in the reconstruction, MIS5E and MIS11, with, of course, very special orbital conditions. They show very, very different amplitudes here relative to the simulation. That's something to keep in mind. But nevertheless, if we look at the paleo range of about 5.5 degree, glacial to interglacial, that matches quite well with recent constraints. And now we can just argue, okay, because we get this overall range reasonably well, we can also run the same model into the future for different scenarios. And there we can see for an RCP 8.5 scenario or SSP 370, we get about 4 degree warming until the end of the century. So this is some kind of, if you like, paleo calibration of the future climate sensitivity, but that needs to be refined much more. And again, I should say these runs completed only 3 weeks ago. So all the analysis that I'm presenting here is preliminary. We are just working on the first manuscripts. All right, polar climate, of course, we want to compare the amplitude in Antarctica. And also there is an overall good match, except for some of the very strong peaks that don't come out. There are maybe good reasons for this. 0.6 degrees always missing in our case because of the sea level, but also the ice sheet itself may have had changes in altitude and so on. There are other reasons why there is not a perfect match here, but something to further investigate. Greenland, of course, only goes back to the Eemian, but this is the Barker reconstruction. For what it's worth, we can say, well, at least the variability comes out quite nicely. And of course, our model does not include the millennial scale variability. We did not play around with freshwater forcing, and I should also say that the freshwater forcing from the ice sheets is not included in our model. So that's another caveat, of course, but in order to do it properly, you need a fully coupled simulation. We are not there yet. All right, then showing again EUFs, just to give a quick overview. Polar climate, this is the sea ice concentration. We see the dominant EUF is, of course, homogeneous in both hemispheres and illustrated here by the principal component, the blue one. We see, of course, the 100K variability, but there is another interesting EUF which also explains quite some variability, which has some kind of combination. In particular, here in the early Pleistocene, we see much higher frequency variability, and here this has a different phasing. So that's something to keep in mind, that we still have other orbital scale modes in sea ice that are related to probably changes in wind and so on and so forth. Also very preliminary and needs to be investigated further. One thing I found interesting is that the MRS9 comes out here in the first EOF as a period with the lowest sea ice concentration. So high value, high PC times negative is lowest sea ice concentration. And that, of course, is understandable because it was also the period with the highest CO2 levels during the late Pleistocene. And now, yeah, global hydroclimate variability plays an important role for our research because we are interested in the early human evolution. And what we see here, dominant EUF, again in blue, is a strong precessional cycle. There is a downward trend. And we have, in particular, this 100K packaging of the precessional cycle and also the longer term 400K precessional cycles, which are much stronger than the 100K ones. That's something to really keep in mind, very much overlooked in much of the paleoclimate literature. Tropics, tropical winds, and so on, they have this very strong 400,000 year envelope cycle. The second EUF is in principle, it's just a CO2 type of signal with a bit of precessional stuff in there, but the pattern is very similar to what we know as the wet gets wetter and dry gets drier pattern. So essentially following what we would expect for the CO2 signal. So not surprising there. And of course, we need to validate the runs against paleo proxy data. So what we have here is North African hydroclimate compared against some dust records, precipitation, The long-term trend is missing, interestingly, in our blue simulation, but the envelope, again, the 400,000 year cycle comes out quite nicely. So we are seeing that actually in general, that overall these long-term trends in the precipitation over Africa are missing, even though they're very pronounced in the lake data, reconstructions, and so on. So we were wondering if there is maybe an effect of vegetation and C4 plants here. Tropical SST looks quite nice, actually, in comparison with the Timothy Herbert reconstruction. However, then in the early Pleistocene, we see that the pacing does not really fit. And it turns out that actually the Willite and Ganopolsky forcing has a very strong precessional cycle in the CO2. That does not seem to be really consistent with the temperature data that we compare our runs with. All right, so but the overall range also in the tropics seems to be reasonably well matched. So I think we have a relatively realistic amplitude range here in this experiment. Just wanted to say a few words about this hominin and megafauna modeling. Again, we use the output. We have a simple downscaling method, and we take fossil data from essentially 6 types of megafauna. I will show that later. 6 hominins, so early Homo members of the Homo genus. And we also developed a simple biome model using essentially Mahalanobis distance habitat modeling. In the meanwhile, El Casella has also conducted a 2 million year experiment with biome 4 offline. Here's just a little glimpse of what this biome variability looks like. Just looking at the last 200,000 years, you see the ice sheets, the deserts expanding and contracting. So this is all kind of relevant for understanding also pollen data and so on. And we're going to look at diversity and fragmentation. Then using about 3,000 fossil data points for hominins, 6 hominin groups, we have developed these habitat maps. Habitat map is essentially, we have a fossil, we know the location, we know the age, so we can look in the climate model, what are the temperature and precipitation conditions and some other climate factors. And these ones we then run forward in time to extrapolate the habitat. This is, for example, we did this first for megafauna, so you can see the average these are the fossil data points actually that go into this habitat model. And these are the averaged habitats, so of course they agree well with the fossil data. But now we can also run this forward in time. Here you can see the evolution of the mammoth habitat. So 1 means it's a suitable habitat, 0 means you won't find any. But again, this does not mean, it's just a suitability. It does not mean there are mammoths actually at that time. And you see there is actually no disappearance here. So even under present day conditions, they would be doing totally fine. So climate control is perhaps not the only reason that killed off the mammoths. So of course, we know the story, Homo sapiens also contributed to this. And again, this is the averaged habitat in the Northern Hemisphere for all of these megafauna groups. And you can see the large drop here during the last glacial period in the habitat. Some of the groups, actually the musk ox, for example, woolly rhinoceros, they had massive drops in their habitat, almost completely lost during the last glacial maximum. So even though we always associate them with ice age mammals, but actually they were suffering a lot. Their habitat was very short. But of course, we know Homo sapiens, if we then calculate the habitat of the early Homo sapiens and other hominin groups, they were doing totally fine in the Northern Hemisphere. They started to enter Eurasia, of course, around 60,000 years ago and became the top predator, which could have further pushed down the climatic habitat loss of mammoths and other megafauna groups to extinction. just a very quick one. We do the same thing for the megafauna. So here again, you can see, sorry, for the hominins. Here you can see all the fossil evidence for the different groups: Sapiens, Neanderthalensis, Heidelbergensis, Erectus, Habilis, and Ergaster. And we can also look at the time evolution at critical points in the Paleo anthropological record. So here we have a very famous site of one of the earliest archaic Homo sapiens skulls, Jebel Irhoud in Morocco. And this guy apparently lived under very habitable conditions. According to our model simulation, we can look at the glacial migration corridors. So there are some surprises which we try to understand. In Lake Turkana, so Central Africa, we can see for the very early groups, Homo habilis, probably our real ancestor, and Ergaster, we see these strong precessional cycles in the habitat, shrinking and growing, and we see the 400K cycle. So interestingly, at this constriction here of the 400K cycle, there was a major extirpation or extinction event. Right, and so on and so forth. So then, are you still there? Ah, okay. I just lost all the videos. Homo sapiens habitat now simulated. We can also now study when are suitable corridors to cross, for example, from Northern Africa into the Levante region. Interestingly, or I was quite surprised to see that there is a lot of precessional variability in the habitat suitability. And again, habitat does not mean there were people, it's just a potentially suitable site. So that's something that we try to combine now with more sophisticated forward modeling exercises with hominin models. Neanderthals, I will just quickly skip. I'm running out of time. And just wanted to show all the data will be made available on our climate data web server. So here is the address, and they're not there yet, but other simulations might be of interest to some of you. Regarding the current data availability, we are very much interested in collaborating. And if any one of you is interested in the data and in collaborating with us intensely, please send me just an email. I will sign out of our meeting quite early because it's very late here. And we will have the data release to close collaborators in April, May, and eventually the data will be released to everyone in October. So that's the current plan. Thank you very much.
Thank you, Axel. That was a very interesting talk. And now we can have some questions. I'll look for the raise hand in the chat. And Christoph Reibel first.
Hi, Axel. Thank you for this nice overview, and certainly I'm of interest, or the data is of interest for the community and also for our group here in Bern. So the question is, at which time resolution have you saved the data? Is it monthly or is it yearly data?
Yeah, so we have monthly data, and we also have some higher resolution atmospheric fields. But I think, yeah, even monthly data is interesting. It's going to be 4.8 million monthly data points. So we are looking at monthly ENSO right now, and the time series is 4.8 million months long, which is interesting for wavelet programs and so on. But yeah, so yeah, definitely not yearly, but we have so the standard CESM output was activated. So there is this one switch that we saved.
Perfect. Thanks, Axel.
Jean, you have a question?
Yeah. Hello, Axel. Thanks for
John.
sharing with us exciting results. I have a question regarding the climate sensitivity and your approach of this 1.5 factor for the greenhouse gases. Do you know the ECS at the T31 resolution?
I don't know at the top of my head, but I think it was quite low. It was under 3. So we did
okay.
these experiments with the same model version earlier, and I think it was maybe 2.9 or something like this. It was barely scratching the kind of IPCC range.
Okay.
And also we conducted an LGM experiment, which also showed very little, I mean, too little cooling as compared to the reconstruction that I believe in. So that's why we decided, rather than fiddling around with the model physics, which can take forever, and it's not going to resolve things, we just intensify the amplitude, glacial interglacial amplitude of the forcing. I know it's a fix, but it's reasonably well if you remember what you did.
Yeah, overall that makes sense. If you run the model in the finite volume dynamic core with, say, 1 degree or 2 degree resolution, the ECS is around 4, and you won't have problem to get the magnitude of LGM cooling.
Right, but then it will be computationally even more intensive. So we played around with all kind of resolutions. 300 year per day is the maximum we could squeeze out of this T31 resolution. And it turns out, because I'm interested in ENSO, this is a really nice model for ENSO as compared to the high resolution versions, which have too strong ENSO variability. So I think it's a good compromise for our purposes.
Yeah, thank you.
And Thomas Stalker has a question, has his hand raised.
Yeah, thank you very much, Axel, for this fascinating simulation. I enjoyed your talk, great. You have this technique of running 21 parallel simulations, essentially each 100,000 years, I guess, or something like that. I'm particularly interested in the change in dynamics during the mid-Pleistocene transition, where you go from a 40,000 to 100,000 year cycle. What can you say about that dynamical change in your setup, where you essentially prescribe in which dynamic regime you are, if I've understood that correctly?
Yeah. I would say in our simulation, this is the transition is fully prescribed by the forcings. There is no internal dynamics that suddenly creates the switch. It's all in the CO2 and in the ice sheet forcing.
And the ice sheet, yeah.
And,
okay.
so
and that comes from Climber, the latter one.
And their argument that there is a change, a gradual decline in CO2, and the regolith also changing, and then your ice sheet starts to wobble in a different rhythm, and also the CO2 will eventually follow. So if you are wondering what the potential physics is, the Climber one is the better one to look at for the Earth system feedbacks. I think ours is more a response experiment in some way.
Thank you, Axel.
Axel, there are also several comments in the chat. I know it's late, but maybe you have time to address them too.
I will stay on and address the questions, and anybody just can send me email to my email address.
Yeah, thank you. Thank you very much.
Thank you for staying up late. That was really exciting new results. Thank you.
Thank you, everybody.
Our next two talks are recorded talks, and so I do think they give us a little bit of time, since the speakers will not be able to answer questions, and they are within the time. So just bear with us as we attempt to share our screen and get the talks going here. The first one is from Lian Ning from Nanjing Normal University. His talk is on multi-scale climate variability during the Holocene, a new group of simulations based on CESM. Okay, I'm going to share my screen, try to figure out where this talk is. Right here. Okay, just a sec. Okay, does everyone see that slide? Can you see it, Arnie?
Yeah, I see it. Yes, thank you.
Okay, I'm going to begin.
Good morning, everyone. My name is Liang Ning. I'm from Nanjing Normal University and also UMass. First, I want to thank the organizers to provide this opportunity to share the recent results from our research group. The topic today is multi-scale climate variability during the Holocene, a new group of simulations based on CESM. Here is the outline of my talk. First, let's take a look at the motivations. We all know that the global mean temperature has raised about 1 degree since 1880s. This temperature increase has resulted in substantial increases of extreme climate events such as heat waves, extreme precipitations, and drought. Usually, this warming is attributed to the increases of greenhouse gas concentrations due to the anthropogenic CO2 emission. However, if we look into the history, we can find several similar warming periods in the history, such as the medieval climate anomaly around 1000 years. These warming periods were caused by natural forcings. The spatial patterns of the medieval climate anomaly are different from the present warming periods. This indicates the influences from the natural forcings and anthropogenic forcings are different. So this raises the first scientific question: how to differentiate the influences from the natural forcings and anthropogenic forcings? During the Holocene, there was also a millennium scale warming period, the Holocene climate optimal. It was first defined between the 7 to 4.2 kbp. However, different reconstructions do not agree with the timing of the Holocene climate optimal. For example, in Charquin and Marcos reconstructions, the Holocene climate optimal locate on the early Holocene. Well, in the new synthesis of Kaufman, the Holocene climate optimal locates at the middle Holocene, and different locations have different timings. Back to the Holocene conundrum. For now, we think it's due to the difference between annual temperature and seasonal temperature. Recent results show that models simulate increasing trend of annual temperature through the Holocene, driven by the retreating of ice sheets and raising greenhouse gases. This raised the second scientific question: when is the Holocene climate optimal? What are the contributions from different external forcings? Meanwhile, there are several millennium scale climate extreme events, so-called bound events. This figure is a new stegmat reconstructions of bound events. From this figure, we can see the evolution of the 4.2 kbp event is different from the other bound events. So this raises the third scientific question: what are the mechanisms behind the bound events? To answer these questions, we designed two groups of experiments. The first is the new NNU Holocene experiment. The second one is the NNU 2K experiment, which was finished several years ago. Both experiments were based on CESM. In each group, there are a control experiment, several single forcing sensitivity experiment, and one all-forcing experiment. This table shows the NNU Holocene experimental design. It includes a control experiment, one orbital parameter sensitivity experiment, one solar radiation sensitivity experiment, one greenhouse gas sensitivity experiment, one LUCC sensitivity experiment, and one volcanic eruption sensitivity experiment, and also the all-forcing experiment. These are the external forcings used in the experiments. All the experiments were integrated for 12,000 years. These are the time series of the external forcings. This table shows the NAU2K experimental design. It includes one control experiment and one solar radiation, one volcanic eruption, one greenhouse gas, and one LUCC sensitivity experiment. It also includes a combined natural forcing sensitivity experiment and one combined anthropogenic forcing sensitivity experiment, and also the all-forcing experiment. These are the external forcings used in the experiments. And all the experiments were integrated for 2,000 years. Here are the time series of the external forcings. Based on the NAU Holocene and NAU2K, and also the trees, CESM, LME, and PMAP3 archives, we investigated the influences and the mechanisms from the natural and anthropogenic forcings on the multi-scale climate variability during the Holocene. These results were sorted from millennial scale to interannual scale. The first results are about the millennial scale climate response to external forcings in NAU Holocene. In reconstruction, the northern hemisphere middle latitude precipitation increased through the Holocene. This increasing trend was captured by the trees and NAU Holocene. Well, this trend mainly located on marine areas. When comparing the middle latitude Eurasia land and the North American land, we found that the driving trend over Eurasia is stronger. This trend is induced by the orbital forcing. Well, greenhouse gas concentrations induce enhanced precipitation in Eurasia, but it cannot offset the negative contributions of the orbital forcing. The response of the precipitation to the orbital forcing and the greenhouse gas is strongly model dependent. We then investigated the northern hemisphere land monsoon precipitation changes in response to the Green Sahara during the Middle Holocene. When the Sahara vegetation and dust reduction were taken into the considerations, the simulated monsoon precipitation increased about 33%, consistent with the proxy reconstructions. After the Sahara vegetation collapsed during the Middle Holocene, the Middle East climate shifted from wet to dry, as found in the reconstructions. This drying trend is not because of the changes of the North African monsoon and the Mediterranean climate. It's mainly because the changes of the moisture transportation from the Red Sea and the Mediterranean to the Middle East. We all know there are 9 bound events during the Holocene. Among these bound events, one famous event is the 4.2 KABP event because it has serious influences on collapse of the Akkadian Empire and many other old civilizations. Based on model simulations, we found that the 4.k BP event may be induced by a multi-century scale fluctuations of the Atlantic SST and also the A-mark strength, superposed on the steady decline of the SSTs and the reduction of the A-mark led by the long-term changes of the orbital forcing. We also compared the 4.2K BP event and the 8.K BP event. In the 8.2K BP event, we know that the A-mark first collapsed due to the meltwater injection, and then the SST changes, and then the NAO change in response to the SST. Well, in the 4.2K BP event, the NAO first change, then leads to the SST changes, and finally make the A-mark change. Besides the centennial scale megadraws, there are also many decadal scale megadraws influencing the old civilizations, such as the megadrought during the early middle 7th century BCE contributed to the eventual political and economic collapse of the Asur. In China, the Ming Dynasty megadrought around 1640 also contributed to the collapse of the Ming Dynasty. We first evaluated the performance of the GCMs in reproducing the characteristics of the megadroughts over the Eastern China. We found the model can reproduce similar frequency, duration, magnitude, and also the mechanism behind the megadrought. We then found if the volcanic eruption was imposed on the control experiment, the frequency of the megadroughs reduced. This is because the megadroughts are associated with a positive PDO-like SST anomaly pattern. Well, after the volcanic eruptions, if we remove the global cooling, we can find that there is a negative PDO-like pattern over the North Pacific. And this SST pattern will reduce the occurrence of the megadrought over the Eastern China. Then, how about the volcanic eruptions occur during the megadroughts? For here, we did a case study, the Ming Dynasty drought. The Ming Dynasty drought is the most severe drought over China during the last 5 centuries, and it may have contributed to the collapse of the Ming Dynasty. We found the Ming Dynasty drought is coincident with the volcanic eruption at 1641 at Mountain Park. But we found only volcanic forcing or only internal variability cannot trigger a drought as severe as the Ming Dynasty drought. Only when the internal variability combined with volcanic forcings, there will be a drought as severe as the Ming Dynasty drought. We then confirmed this mechanism through a group of sensitivity experiments. We first picked 15 droughts from the control experiment. We then implement the forcing from the Mountain Park volcanic eruptions at the last year of the drought. We found the drought persists 3 more years with severe magnitudes consistent with the history. And this paper was selected by the Nature Research Highlight. We also further tested different cases in which the volcanoes erupt at different stages of the drought. We found that the influences are most serious if the volcanic eruptions occur at the late stage of the drought. This is because of the changes of the soil moisture. Okay, I think I need to go through the rest results first. This part result is about the influence from the LUCC. First, we found the LUCC can induce a centennial scale cooling trend. Well, over the eastern China, after the LUCC change, we can see the leading pattern of the decadal precipitation changed from the dipole pattern to the triple pattern. This because the increases of the probability of the antiphase of the PBO and AMO. Okay, this part results is about the influence from the solar radiations. First, we found a centennial episode of weak East Asian summer monsoon during the medieval climate anomaly. Then we found the decadal variation of the East Asian summer monsoon and also the winter monsoon are dominated by the 11-year insolation cycle. Okay, the last part of the result is about the influence from the volcano eruptions. First, we found there is a La Nina-like state in the second year after the strong volcanic eruptions. We then investigated the different influences from the northern high latitude volcanic eruptions in different seasons. The January eruption can induce an El Nino in the same year, while after the October eruption, there will be an El Nino in the second year. Well, there is usually no El Nino event after the April and July eruption. The mechanism are achieved through the Northern Pacific cyclone and the Asian monsoon. Then we also investigated the asymmetry of the temperature evolution and duration between the Arctic and the Antarctic. Here are the concluding remarks. I think maybe I don't read through it. For more information, you can check our publications since 2017. I think that's all my talk today. Thank you for watching. For comments and questions, please contact me through my email. Moreover, we are organizing a special issue on the atmosphere. If you have suitable manuscripts, you are welcome to submit to this special issue. Thank you.
Okay. And okay. I think if anyone has questions they would like me to forward to the speaker, you can put them in the chat and I'll pick those out and ask the speaker to get back to those individuals. Our next talk is also a recording by Kefan Chen, who's in the same group as Lian Ning from Nanjing Normal University. The title is "One Drought and One Volcanic Eruption Influenced the History of China, the Ming Dynasty Mega Drought." So, let's see.
Good morning, everyone. My name is Kefan Chen from Nanjing Normal University. It's my great honor to be here to give this presentation. The title is One Drought and One Volcano Eruption Influenced the History of China, the Ming Dynasty Map Drought. This is the outline. First is the motivation. The Ming Dynasty map drought occurred at the end of the Ming Dynasty and is one of the most severe drought events in China in the last millennium. This unprecedented drought occurred in 1637 to 1642 against the background of the late Ice Age. During this 7-year-long map drought, aridity, famines, and disease prevailed, contributing significantly to the collapse of the Ming Dynasty in 1644 and casting profound impacts on Chinese history. Many efforts are devoted to studying the mechanisms behind severe drought events in Eastern China, like the Ming Dynasty drought. Previous studies confirmed that volcano droughts in Eastern China are primarily caused by internal variability. On account of this, external forces such as strong volcano eruptions can also drive serious rainfall deficits in Eastern China in multiple timescales. For instance, on the Keynote timescale, volcanic eruptions can influence Asian summer monsoon by enhancing the Atlantic multi-decadal oscillation as well as connective PBO patterns. On triennial timescale, volcanic eruptions can influence onset events and result in precipitation decreases in monsoon regions. Some studies also assume that the Ming Dynasty map drought may be related to volcanic activities. However, the mechanisms triggering and maintaining the Ming Dynasty map drought has remained elusive. How do these map droughts become so severe and take so long? To solve these problems, in this study, we investigated the mechanisms behind the Ming Dynasty map drought from the combined effects of internal variability and volcanic forcing, which is of great value to drought prediction and disaster calculation in the future. Next is methodology and data. In this work, the reconstructed data we used include the drought index in Eastern China and precipitation in East Asia. We also use simulated data from the CESM last millennium ensemble. Besides, we reproduced the Ming Dynasty map drought by volcanic sensitivity experiments based on the Community Earth System model. The ice core-based volcanic aerosol reconstructed by Paleo is used as the external forcing in sensitivity experiments. In this paper, we define drought as negative precipitation anomalies lasting for about 5 consecutive years, with the maximum precipitation anomalies lower than 1 standard deviation in Eastern China. The North China Plain and Sahara area are studied in our work. These are our results. Firstly, we investigated the evolution characteristics of this map drought. In this figure, the blue lines are the changes of precipitation in reconstructions. The red line indicates the magnitudes of eruptions. This figure shows significant precipitation decreases during 1647 to 1645. The decrease magnitude is close to 3 standard deviation and is one of the largest drought events in China in the past 500 years. According to these reconstructions, there was no strong external forcing event at or immediately preceding the onset of the map drought at 1937. Also, the precipitation minimum, which occurred in the middle of the drought around 1641, coincides closely with the year of eruption of Mountain Copper. The dry conditions persisted years after the eruption. These features lead us to hypothesize a superposition mechanism for the mean dynamic map drought, that this drought was triggered by internal eruption in 1637 and was then amplified and extended by the eruption of Mountain in 1641, generating a 7-year-long map drought event. To verify our hypothesis, we studied the different periods of internal volcanic forcing and their combination to this map drought. This figure is one of the member Reynolds Paleo test for 1,000 years of CESM control run. The right figure is the probability of drop frequencies based on the 2,000 realizations. 2,000 years, there is only 10% occurring probability of one map drought of 7-year length and above this signal tested as a major event. Map drought event like Hemisphere map drought has a small occurring probability caused by internal climate changes. The superposition of volcanic impacts on natural drought event probability of like the mid-dynasty map drought. Then, by comparing drought events with and without, the blue lines represent the ensemble mean precipitation anomalies centered with volcano eruption and then strengthened by the Lgm Simulations during the past millennium. This figure shows the ensemble mean of drought events through the nature volcanic forcing only.
Seems to be cutting out.
Shows a weaker and short. The precipitation decreases only occurred on the eruption. Drought after volcanic eruptions. Okay. Without external period of the mean dynasty map drought, then the volcanic
Okay, I paused. Is the presentation cutting out for everyone?
No, I think it's still going on, but I think maybe the transfer rate of the presentation, because it's probably a large file, is slow.
You know, it's probably okay, Esther, because she has such good slides. We could just follow the slides without the voice.
Yeah,
that would be best. Yeah,
I paused it. It has 6 minutes left. So we should finish at about 9:40. So I'll get it going.
Major events tend after volcanism. It's level.
Okay. Well, that was too bad. And again, any questions for the speaker can go in the chat, and I don't mind forwarding those on. Our next speaker is Deepak Chandan from the University of Toronto. He will be speaking on the African humid period, precipitation sustained by robust vegetation, soil, and lake feedbacks. And I believe, here we go.
Hi, Esther and everybody else, can you guys hear me?
Yes.
Okay, that's wonderful. Is the sound quality okay?
Yes.
Okay, that's great. Thank you, Esther and Arnie, for having me for this talk. Deepak, I'm a postdoctoral fellow at the University of Toronto. And the major content of my talk today is going to be on the ability of land surface feedbacks to sustain the precipitation during African humid period. This is the content of a recent paper that was that came out in GRL. And I will then talk a little bit about some of our ongoing work on mid-Holocene, Africa and other parts of the world. So let me just dive right in without much introduction to Holocene. You all know about the Holocene quite a bit. The African humid period, otherwise also known as Green Sahara, has plenty of evidence in record. There are vegetation reconstructions, Paleo lake reconstructions, river valleys, various archaeological findings, cave paintings, etc. So a lot of lines of evidence point towards the fact that the Africa was much greener than today. As being one of the most distinctive features of mid-Holocene, a kind of green Sahara compared to what the Sahara looks like today, it has attracted a lot of attention and rightly so. And through the several decades worth of studies, we have found that the importance of feedback in the climate system is important to greening the Sahara. Ocean feedback, obviously, there's dust feedback, and there's feedback from the land surface. The orbital changes itself, which actually initiate the monsoon, are relatively minor in the contribution, and the feedbacks are very important. So they have been very extensively studied, but there are a couple of issues with the original studies. So the land surface feedback comprises feedback from vegetation, soil, and lakes primarily. And so very few of these studies have considered the collective impacts of these feedbacks together. Many of them have been sensitivity studies that have individually looked at one of the components, but very few of them have looked at them together. And those who did look at these are actually quite old by now, and there hasn't been much work on this in the last few decades. So most of our notion for how strong what is the understanding of these, the understanding of these feedbacks and what their strength is based on models that are quite old and do not really aren't able to quite constrain the ability of modern coupled climate models to simulate these feedback strengths. So we went back to directly look at this scenario and see how a modern coupled climate model using modern reconstructions for the mid-Holocene surface reacts, and what are the differences compared to the older simulations. So we use our model, which is a U of T version of CESM4. It's a slightly modified version of CESM4. Modifications are restricted to the ocean. And we run our simulations at 1 degree resolution. And we have several simulations, but the key simulations are shown here. One is a PI reference, also known as a PI control. And then we have a mid-Holocene control, which is only forced by mid-Holocene trace gases and orbital configuration. Then we have a simulation in which we add vegetation changes to the reference simulation. And then we have one in which we add on the soil changes to the previous simulation. And then we add on the lake changes to the reference and vegetation. And then we have one that incorporates all of these feedbacks together. So vegetation, soil, and lakes. I'm showing you some plots here for how we have made changes. Some of these are quite detailed. I'm not going to go into much detail here, but just to show you the idea of what the changes entail. We have I mean, each grid cell is obviously occupied by several different plant functional types, but here I'm just showing the majority plant functional types. So we have a greening, we have a northward extension of vegetation, starting with more like tropical forest vegetation and then slowly transitioning to grasses. And then we have these various lake distribution for the mid-Holocene, mostly dominated by the large megalakes that were present. And we also changed the soil and in which we reduced the albedo of soil, which we changed the CLN soil color that reduces the dry soil albedo from 18% to 9%. So in the presence of the orbital forcing only, which is a reference simulation, we see broadly in the annual mean a cooling over broad parts of Africa and Arabian Peninsula. This is driven by increased cloud cover, and we see greater precipitation. And in these two plots, I'm going to show you the zonal means of the precipitation and the zonal mean anomaly from present day. So you can see that the present day, which is the black curve, matches pretty well with GPCC through most of the Africa, but it obviously, as many climate models, overestimates the precipitation in tropics. But only in the presence of the mid-Holocene reference simulation, there is a slight enhancement to precipitation throughout Africa in the zonal mean, and the net increase is shown here, just about 200 millimeters. So not a lot, but it does increase the precipitation, just like most simulations have always shown. So in the presence of vegetation, the Africa is not cool overall. There is warming over here because of the decrease in albedo, but there is still cooling over in the tropical band due to increased precipitation. And that increased precipitation is seen here. You can see that is much more intensive. And now we're actually beginning to reconcile with both precipitation and temperature proxies. And in the zonal mean, you see that there is a much significant increase in precipitation, especially in the Sahelian region, which is shown by this anomaly here. We have over about 600 millimeters of increase in precipitation there. So we're beginning to do much better now with vegetation feedback. Once we include the soil feedback, then the warming over Sahara increases much more. And in the Arabian Peninsula as well. And precipitation increases much more, very much the shiny effect. In the zonal mean, you see that, again, there is a much marked increase in precipitation. This is the new curve here. And the anomaly with present day is much higher, just under 800 millimeters. And we also getting much more precipitation in the higher latitudes of Africa than previously. Now, in the presence of just the lakes and vegetation, the patterns are very much similar to vegetation. There is not a whole lot of difference compared to what was obtained with vegetation only. So if you compare the violet curve here and the pink curve here, I'm not very good at colors. I think that's pink. There's not much difference between the two. They're relatively similar. There's some increase in precipitation in the lower Sahel region. There is some increase in precipitation in the northernmost areas of South Africa because of the presence of these moisture sources. But overall, the results are very similar to vegetation. But an important thing that does come up now is that you're starting to see a little bit of heterogeneity in temperature field, which was not present before. Before in the presence of soil or so, I mean, except for this region. Overall, there is the temperature change over Africa is very zonally uniform, essentially. But now in the presence of more cooling centers, you can see that there is some heterogeneity, which can help us better agree with proxies. Now, with all the feedbacks together, so orbital, vegetation, soil, and lake, this is the net annual mean temperature change. And this is the net annual mean precipitation change. So if you look at the temperature, we are doing relatively good, actually. We've got these 3 key centers in Africa. By the way, you guys are able to see my mouse, right? Okay.
Yes.
So you have these 3 centers here that are constraining mid-African temperature, and we are really nailing that very well. And this center of warming is just south of this Lake Fezan here. We have warming here, which is matching what we are getting, just a transition region. We're not getting a good warming here, but it's still just, there's a warming. We're not getting the cooling here, but we are just, the cooling center is just south of that. So it might be some local effects. We're constraining the transition temperatures here between the cold, warm, and the cold. We're getting broad some cooling here around the lake. We're getting cooling in most of these tropical regions, just as the precipitation proxy suggests. There's a lot of variability here, which might be due to local processes. We're getting the right temperature here. We're getting right temperature here. These are coastal effects, and we're not matching here, but that might be, again, it might be due to, again, local forces that we are not able to constrain. So very limited reconstructions, but we are basically getting the transition regions and the core strengths quite accurately. And same in precipitation here too. We can see this precipitation proxy in many different ways. You can see here in overall the green curve is the total feedback, which is very close to that you get from soil. The overall precipitation extends very far into Africa. And in the zonal annual mean, we are getting about 800 millimeters per year anomaly, increased precipitation in the Sahel region. These magnitudes are all significantly higher than have been reported in previous studies, except for the recent studies, which is involving green Sahara and reduced dust. So we can see proxy data comparison again for precipitation in this way here, just like Francisco Posada and colleagues have done for the EPSL paper. The proxies are aggregated in 5-degree latitude bands, and these are shown here by the red circles. And the model anomaly at those locations from this MVSL model is shown here, and you can see that we are matching extremely well the data difference, data model the comparison to data actually. Again, in this region, our model, just like other models, show much higher precipitation than that, which is suggested by proxies. And so there is still that issue that needs to be resolved. Obviously, marine proxies show from cores right off the coast of Africa that there was very high precipitation, even higher than what we can reconstruct here, whereas land proxies show usually more modest increase in precipitation. Our results are somewhere in between those two things, but otherwise a pretty good comparison. So now I will talk a little bit about the ongoing work. This is not the topic of the paper that was in the GRL, but the GRL result was just our first step into a bunch of work that we are doing, and you can expect to read from our group in due time. So we are continuing refinement of green Sahara land vegetation. So I have several new simulations where I have refined the vegetation and soil properties further, especially by incorporating east-west vegetation asymmetry and a more appropriate land surface treatment for the Arabian Peninsula, including treatment for the Rub al Khali Desert. And overall, the results for these are very consistent with the previous results, but reduced precipitation in the Arabian Peninsula actually leads to more increased precipitation on the western half of Africa. So it actually can help actually improve the ability of vegetation to sustain on that side of the continent. So I'm currently running similar sensitivity studies for vegetation changes in the Northern Hemisphere. So we have complex regions of vegetation changes, and there are lots of simulations where I have performed the vegetation changes over Eurasia only and over North America, and then the combined vegetation. So these simulations, some of them have just finished and some of them are finishing, and we'll be combining the results into a paper very soon. And then we are looking at the impact of, in our group with other students, impact of green Sahara on the Indian monsoon and the dynamical downscaling of Africa over Mediterranean and connection to early human settlements. This is actually the reason why we are funded, and I'll talk about these two things a bit right now. So the first thing is the connection of the green Sahara impact with the impact of Green Sahara on the Asian monsoons. And this has been a subject that you have seen today in an earlier talk, and something that Clay Tabor and colleagues have just released in GRL in October. And we were working on it about the same time, actually. So just like Clay Tabor and colleagues and the other talk that was earlier today, we're also finding that there is an influence of increase in the West African monsoon with an increase in the Indian monsoon. So it is an increase in both the reference case and when we apply the Green Sahara. So when we apply the Green Sahara, it increases much more. So we are looking at it not only from a global perspective, but from a dynamical downscaling perspective. And this downscaling work is really done by Yiling Huo and group who is connected to talk today. And she has written up this paper that we are just about to submit to CP. And what we have done is that this is the global grid, the atmospheric grid, and we have embedded a high resolution WRF 30-kilometer grid to downscale our simulations. And we have coupled that within a downscale high resolution ROMS grid as well. So it's not just an atmospheric downscaling. This is the high resolution ROMS grid that is embedded over the South Asian region, and there is a full coupling between the atmosphere and the ocean. And this leads to some very interesting results that I will show you. So first of all, the downscaling obviously increases the fidelity of reconstruction in the region. This is the U of T CESM4 reference SST anomaly, and this is the one obtained with WRF and Croker. You can see there is much more features, especially a lot more Ekman coastal effect from the winds, from the strengthened monsoon winds, which the global model is obviously not able to capture. So we can capture a lot of coastal processes here with the ROMS model. In the SAT as well, this is the global model temperature anomaly between the reference simulation and PI for June, July, August, September. And you can see there are these features, but they are coarser compared to what a high resolution downscale model can simulate. And you can see there are significant differences too. For example, over India, the temperature is higher as cooler. And you can see that the temperature anomaly simulated over the Indochina Peninsula is different between the global and the regional model. This warming center over Tibet also protrudes for the south in the dynamical downscaling version. And all of these has implications for data model comparison. So now I'm showing you precipitation anomalies between the global model, precipitation anomalies between the mid-Holocene simulation and PI compared to Barthelin et al. Reconstruction. And the left-hand side is the global model, and on the right-hand side is the high-resolution downscale model. On the top row are the anomalies from the reference simulation only, which does not include the effect of Green Sahara. And in the bottom row is the simulation with the Green Sahara. So you can see, first of all, that without Green Sahara, we have some improvement in precipitation, but it doesn't really penetrate the Tibetan Plateau and the Central Asia region or over Eastern China very much. The downscaling does improve over the ability of the global model to reconcile with data. There is some improvement with data model comparison in the downscale model, but overall the precipitations are much lower than what is suggested by data. Now, if you look at Green Sahara, we can see that even in the global model, there's much increase in precipitation. This is essentially what others have found too, and you are able to reconcile better with the proxies than without Green Sahara. But now if you look at the dynamical downscaling in Green Sahara, you're able to see that it further increases the comparison with data significantly more. Like you have not only additional features, but if you look at all this region, you have increased precipitation in the lower Himalayas. You have these bands here, which are basically the Kunlun Mountains, the Tian Shan Mountain, and the Pamir Mountain Range, which is where these data points are actually situated. And the downscaling produces much better reconstruction with these than the global model. We even get better results here in the northeastern China. Okay, we get better results here in over Myanmar, which we are not able to get with the global model. Remember, these both models include Green Sahara, but this is the global model, and it's not able to match that well with data as the downscale version. And we're doing pretty good here too. There are some sites in the coastal regions. This might be likely coastal effect. That's why we're not able to match this. Our ROMS domain does not extend to this region, but otherwise we're doing significantly better than the global model, even with the Green Sahara. So this is a really important result, and I hope that this will drive the discussions and theme going further, that you really need downscaling in certain parts of the world, especially parts of the world that have complex orography and land surface, to be able to improve upon the data model comparison with the global model. So Yilling is just about to submit the results soon, and most of the downscaling work for the present day monsoon region has been described by her in these papers. And finally, this last thing that I will talk about is our other downscaling work over Africa, where we have currently an 18-member physics ensemble incorporating various...
I think we need to wrap up a bit.
Okay, right. So anyways, this is other work that we're doing for the Mediterranean region, and we'll probably be working on that. This is with Fengizi. And again, we are incorporating a high resolution downscaling in ocean and atmosphere as well. And this is to understand the human settlements in this area. We are being funded by the computational research in the ancient Near East, and we want to understand why people settled in the regions where they settled, and we can only do that with high resolution downscaling. Okay, so to conclude, the likely cause of Green Sahara was obviously the increase in precipitation driven by the increase in summer insolation, but the impact of feedback was extremely important. And with state-of-the-art coupled climate model, the feedback strengths are much higher than what were thought about before, and they lead to better proxy data comparison. Green Sahara leads to strengthening of the Indian monsoon and leads to better data model comparison and dynamical downscaling over Southeast Asia really improves a data model comparison compared to global models. Okay, thank you very much.
Thank you. Questions? Well, I do have a question to your first part of your presentation. Have you looked into the ocean records? So the ocean proxies and maybe also ocean modeling in the equatorial Atlantic, because that could be of interest to understand some of the biases you still have in precipitation.
Thank you for that question. No, we have not done for the current for the previous paper, but it is an objective for me to do in the papers that I'm working on in the new results.
Yeah, that may be interesting to look into.
Absolutely.
Yeah.
Any further questions? We might, I think we should maybe move on. Those questions can go now in the chat. And next we have Zhang Zhu from NCAR speaking about an update on the simulation of the last glacial maximum using the CESM2.
Okay, thank you, Esther. Can you see my slide okay?
Yes.
Hello, everyone. I'm Zhang Zhu, a project scientist here at NCAR. I work with Betty and Esther. Today, I'm going to give you an update on the simulation of the last glacial maximum using CESM2. So many of you may know that CESM2 has an equilibrium climate sensitivity higher than 5. So the value is much larger than any previous CESM models, and it's larger than the published consensus range. And thanks to many papers published, now we have a clear idea that the higher ECS in CESM2 compared to CESM1 can be attributed to the stronger shortwave cloud feedback. But the question remains, is this realistic? There's an interesting paper coming out last year, and they argue that this high ECS is plausible. This concerns that the fact that CAM6 corrected a mean state bias in CAM5. So in CAM5, the mixed phase clouds contain insufficient supercooled liquid, meaning you have too much ice in the clouds. This has large implications on climate sensitivity. So in CAM5, when you have too much cloud ice, as the climate warms in response to CO2 increase, the cloud ice will melt into liquid. This process will reflect more shortwave radiation, forming a negative feedback. So in CAM6, when you correct this mean state bias, you should expect the removal of this negative feedback. So you should expect a higher cloud feedback and climate sensitivity. And this is supported by the present day observation that the high ECS is plausible. Because ECS is a critical metric in climate science, we really need to carefully examine this issue from multiple lines of evidence. For example, we can use the last glacial maximum to inform the ECS in CESM2. So this is not something new. The Paleoclimate Working Group have been doing in the past 2 decades. And you can see that for many major release of CESM versions, we do have Lgm simulation. And you see that when the ECS is higher, you also simulate a greater Lgm cooling. And in the past, the model simulated Lgm cooling more or less fall within the proxy suggested range. And I want to point out that in a recent paper, we refined the reconstruction of Lgm global cooling to be around 6 degrees C, indicated by the black bar here. Next, let's perform CESM2 Lgm simulation and use the Lgm data to inform the ECS. So for the Lgm simulation, I tried to use the CMIP6 configuration as close as possible, including the horizontal resolution. But still, there are some differences, but those differences do not impact the pre-industrial climate state and the ECS. Please refer to my GRL paper for details. And the Lgm simulation followed the PMIP4 protocol. We have lower greenhouse gases and the presence of the Lgm ice sheets. We used pre-industrial aerosol, vegetation, and tidal mixing. Those are important factors, but for start, we just need to keep things simple. And it's also easier for us to attribute the temperature response directly to classical climate feedbacks, such as cloud feedback, water vapor, etc. So the CESM2 Lgm simulation was initialized from the available CESM1 Lgm to save us some computing time. So here I'm showing you the global cooling in the simulations. So those are time series compared with proxy data, the black line here. And the red is the global mean Lgm cooling in CESM2. You see that after the initialization, the Lgm quickly drifted away, reaching a Lgm cooling more than 11 degrees C at the end of the simulation. So this is certainly too cold than proxy. And there's almost impossible to reconcile this model data discrepancy using the proxy uncertainty and also the Lgm boundary conditions.
Something to say?
No, I'm gonna meditate.
Okay.
And the red simulation here is the same, the orange simulation here is the same as the red, except that I used the CAM5 physics package. Now you see that we have a more realistic Lgm simulation, agrees better with proxy and also with the result in CESM1. So this exercise basically tells you that this CESM2 Lgm is too cold and the atmosphere model is the reason. So this slide shows you a more model data comparison. So those are set by set comparison in sea surface temperature. The y-axis is the CESM2 x-axis are different proxy types. You'll see that no matter which one you are looking at, the markers are systematically below this 1-to-1 line, suggesting that CESM2 LGM is too cold. And in comparison, we had a very good model data agreement in CESM1. The root mean squared error is much smaller. And it is interesting to note that the spatial pattern in the SST response is largely similar between the two. To further understand why the CESM2 LGM is so cold, I perform a forcing feedback analysis. For now, we just focus on the climate feedback parameter here, lambda. So basically, you divide the forcing by the global temperature response. Then you can compare this metric across different simulations. You'll see that the climate sensitivity parameter is more positive in CESM2 than that in CESM1 by 0.4. And what is causing this? The next column, I'm listing the shortwave cloud feedback. You'll see that the value in CESM2 is again larger than that in CESM1 by 0.4. So this close relationship connection suggests that the cloud feedback is responsible for the excessive LGM cooling in CESM2. This is not a surprising result. This is consistent with previous studies showing that cloud feedback is responsible for the higher ECS. Basically, our result here suggests that it's also responsible for this much colder LGM simulation. And this column, I'm showing the shortwave cloud feedback in abrupt 4x CO2 simulation. Comparing the numbers, you see that the CESM2 value is also larger than that in CESM1 by 0.4. This close connection can also be seen in the zonal mean shortwave cloud feedback. Top panel is LGM, bottom panel is abrupt 4x CO2. You see that compared to CESM1, the blue here, CESM2 cloud feedback is more positive over the subtropics and the Southern Ocean. You basically see a similar overall feature in the abrupt 4x CO2 simulation. So cloud feedback is is the connection between ECS and the cloud and the LGM cooling. So far I have showed you that CESM2 LGM is much colder than proxy, and the ECS is likely too high, and it's caused by the cloud feedback. The next question naturally you would ask is why we have this strong cloud feedback in CESM2 in Chem6. So this figure is from Gettleman 2019, and they did a very comprehensive examination of the differences between Chem5 and Chem6. They found that how you treat the turbulence and shallow convection, ice nucleation, as well as macrophysics are important for this increase of cloud feedback in Chem6. This is insightful, but it doesn't tell us whether those which schemes give us this problem in the LGM simulation. So follow the Gettleman approach here. I performed a fully coupled LGM simulation to examine different schemes. So here I'm using the 2-degree resolution model because it's faster and it's cost efficient. So the red is CESM2 Chem6. By the way, I'm showing the global cooling again time series. So the red is Chem6. You'll see that when you run CESM2 with Chem6, the LGM will be too cold than proxy data here. The orange is the same as the red, except that I used the older version of the ice nucleation scheme. You see that now you have a more realistic LGM in terms of the global response to the LGM forcing. The green is I use the older version of the macrophysics scheme. You see that we can also have a realistic LGM simulation. The blue is I use the older version of the turbulence and shallow convection scheme. So basically, it makes little impact on the global temperature response. And the purple is I used an alternative way to calculate autoconversion and accretion, just some detail in the macrophysics. In the end, the simulation will still be too cold. So basically, this exercise combined with real-world data from the Lgm suggests that it's likely that the new ice nucleation and macrophysics scheme is responsible for this unrealistic Lgm cooling. Then what's the implication on climate sensitivity? So here I calculate ECS through performing slab ocean simulations. You see that when for the configurations gives you realistic Lgm cooling, you also have much lower ECS. Again, this connection between ECS and Lgm cooling is through the cloud feedback. Showing the figure on the right, the x-axis is Lgm shortwave cloud forcing, and the y-axis is that in the WCO2 experiments. You see a very nice correlation between the two. Of course, there will always be state dependence, meaning that the cloud feedback will be more positive in warming simulation than in cooling simulation. But this state dependence does not vary much across different configurations. That's why in this scenario, we can still use Lgm to constrain cloud feedback and ECS. So here is a quick summary. Lgm is too cold, meaning that the ECS is likely too high. The connection is through cloud feedbacks. And our results suggest that the cloud macrophysics and maybe the ice nucleation scheme is not working well within the current setting of Chem6. And here I want to emphasize that it's relatively easier to perform paleoclimate simulation and see that, okay, there might be something wrong in the model, but it's much harder to provide an improved solution, because if you want to do it correctly, you should be able to meet multiple lines of constraints. For example, a correct solution should simulate past warm and also past cold and also warm climates, should simulate present day observation, including the 20th century warming, and should also agree with process level understanding. So for now, we can maybe still use CESM2 with Chem5, but you should be aware that there won't be a high top model. And we know that the mean state of the mixed phase clouds are worse than Chem6. That's it. Thank you. And I'm happy to take questions.
Thank you,
John.
Yes. Go
sorry,
ahead.
Quick question. Yeah, really interesting presentation. I was wondering, what do your results suggest in combination with sort of the future warming ECS being too high? I mean, do we just not use CSM2 Chem6? I mean, do we just have to sort of throw those away, or do we take it? Are they still useful simulations in the context of other mechanisms?
Yeah, I think that's a good question. And for Lgm, we should realize that we are applying a very big radiative forcing there. So the forcing could be 5 or 6 watts per meter square there. And we believe this is CSM2 simulation is problematic. But for simulations with relatively smaller forcing, it should be okay. And also, even for strong forcing scenarios, maybe some feature, say the spatial pattern, might still be valuable for research.
Awesome, thank you.
Was that Nicholas?
Yes.
Okay. Jonathan? Oh wait, who just spoke?
So Nicholas Heavens, Space Science Institute just spoke.
Okay, so Jonathan Buzan would be the next question. Sorry.
So me.
Yeah, I
Yes.
see your hand raised. Yeah.
Yeah, I just wanted to have a quick little comment. You know, I did some recent work on CMIP5 using scaling techniques of moist thermodynamic variables, and many of the CMIP models all fall within a very narrow range of deltas of their changes per degree of global warming. And I just recently saw some preliminary results on CMIP6, and their deltas are per degree of global warming are very similar to CMIP5. So I wouldn't say that, you know, like CAM6 and things are not useful. They are still quite useful for doing projections and everything. It's just that you can't necessarily use like the absolute values for them. But yeah, that's my comment.
Thank you.
I was wondering whether you have done experiments with increased dust, because the LGM had much higher dust than present or pre-industrial, and so it would be interesting to look into maybe using a realistic dust forcing and see how the climate sensitivity would be with that dust forcing.
Yeah, thanks, Ernie. This is an important point, and we are planning to test that later. Not for now, because not just dust, we also know that other aerosols, the concentration at LGM is also higher than pre-industrial, for example, sea salt, and also the differences in vegetation cover. So those additional forcing might cool the Lgm simulation further. But for dust, we are not sure. We definitely need to test that. But I would say it will be a big surprise if dust can warm the climate by 5 degrees C globally.
Any other questions?
Yes.
Okay.
Nicholas Heaven, Space Science Institute. Okay. Does the CESM2 CAM5 simulation use CLM5?
Yes.
Okay. And I guess the follow-up is that particular simulation archived anywhere yet?
We haven't published the data yet. We are still working on this, and hopefully we can figure out a realistic CESM2 CAM6 LGM and publish the data all together.
Okay.
But that's the plan.
Okay, thank you.
If there aren't any more, I think we should move on to our next talk by Andrea Schmittner.
Esther, Keith Lindsay has his hand up.
Oh, Keith. Oh, I'm sorry, Keith. I didn't see.
I just raised it. Thanks for catching that, Betty.
Okay.
So great analysis. I have a question about more of the methodology of understanding, attributing the error. That sometimes solution A looks better because there's compensating errors in different processes. And if you improve the process in one of them and it removes that compensating errors, it degrades the solution. And it seems like you're now, if that is what's going on here, then you are attributing the error, the degradation of the solution to the change in a process, which actually might be improving the process. While there could be there's errors that are no longer compensating. Have you pondered how to differentiate if that is occurring and hypothesize about what other processes might be playing a role that have compensating errors in your better solution?
Yeah, thanks, Keith, for the comment. I think this is very important, and it's very likely happening in maybe 1 or 2 of the configurations. So that's why we are still working with the Hemisphere Modeling Working Group, trying to check other lines of evidence, for example, satellite observations, and trying to figure out which one is indeed better.
Okay, I think we should move on to our next speaker, Andreas Schmittner from Oregon State University. He's speaking on glacial deep ocean deoxygenation driven by increased air-sea disequilibrium.
Okay, hello everybody. Can you see my screen?
Yes.
All right, so we'll stay with the last glacial maximum, but I'll talk about ocean biogeochemistry and in particular oxygen changes. So what we're thinking is that the observed deep ocean deoxygenation was not caused by changes in the biological pump, but rather by changes in the disequilibrium. And my collaborators here are Ellen Cliff and Samara Kariwala from Oxford University. And this picture just shows sea ice because sea ice has something to do with this increased disequilibrium, as we'll see. So here are just pictures of my two collaborators, and the paper was just published in Nature Geosciences. If you want to read on some details there, feel free to grab that. So the issue is really the oxygen changes during the last glacial maximum. And this figure shows the observations, so reconstructions of oxygen changes in these colored symbols, and the blue symbols indicate reduced oxygen. So that is oxygen gas, O2, in the deep ocean, and red indicates increases in oxygen, and so you see these red, so increases more in the upper ocean, but the deep ocean is generally most of the reconstructions, by far most of them, show reduced oxygen in the deep ocean. And so here's some of the references from the reconstructions. Many people have worked on those, and most of those, I should say, are qualitative. Those are the open symbols, but there are some quantitative reconstructions coming along, but still they have some relatively large uncertainties, I would say. But nevertheless, the consensus from the data is that the deep ocean was reduced in oxygen during the ice age. And that may be at first a little bit surprising because, if you know that oxygen is more soluble in colder water, you would expect that the ice age ocean has higher oxygen. And this may be the explanation for this upper ocean changes, but it cannot explain the reduction in oxygen that is observed for the deep ocean. And so we want to explore this with modeling, and this figure also shows in the color scheme the model simulated oxygen changes, where you can see that our model reproduces the data in that in the deep ocean it does simulate lower oxygen concentrations. And I'll talk a little bit more about the model and the specifics in one of the next slides. But I want to say, I think it's fair to say that the prevailing hypothesis for this decrease in deep oxygen concentration in the deep ocean and the LGM is the biological pump. And here I've just selected a few examples where those authors, talk about the biological pump or soft tissue pump or respired carbon storage, which is essentially all the same, suggesting that the biological pump was increased in the last glacial maximum, and that would explain the lower oxygen concentrations. And that is plausible because the biological pump, moves carbon from the surface to the deep ocean, where then the organic matter is respired and oxygen is consumed in the process, in the respiration process, and turned into CO2. But there is also, if you look in this figure, it shows the biological pump here, but also what controls carbon and oxygen is air-sea gas exchange, because both are gases and both exchange with the atmosphere. And there is an important difference between the two gases that comes in through that gas exchange. And that difference is related to the carbon chemistry. As CO2 enters the ocean, it reacts with water and then forms bicarbonate and carbonate. And so only a very small proportion of the carbon in the ocean is actually CO2, dissolved CO2, whereas most of it is in these bicarbonate and carbonate forms. So this is a large buffer for carbon, whereas for oxygen, we don't have that. Oxygen is essentially unchanged. It doesn't react with seawater. And therefore, its equilibration time is much faster than for carbon. So for oxygen, the equilibration time is about 1 month, whereas for carbon is about 1 year. And this has been known for a long time. Here is this seminal paper by Broker and Peng in 1974 that explains the reasons for this. And as I said, the difference is essentially due to this fact that carbon reacts with seawater, whereas oxygen doesn't. And so for oxygen and this short equilibration time, you can actually see that if you look at surface oxygen concentrations here in the data in this map. So the tropics have low oxygen concentrations and the high latitudes have high oxygen concentrations, which is consistent with a strong imprint of solubility on surface oxygen. And here, the lower right panel shows a figure from Broker and Peng, the tracers in the sea, that influenced my thinking a lot. That shows observations, these dots here as a function, so dissolved oxygen measurements as a function of temperature. And you can see the saturation line here, so that all the data are very close to the saturation line, but slightly above it. And that is the consequence of photosynthesis that produces oxygen at low latitudes and leads to slight oversaturation. But the difference from the saturation line is in the few percent, so it's very small. And that has led essentially to me personally, and I think also the community, thinking that surface oxygen is equilibrated, and so therefore we can use oxygen in the deep ocean. Changes in oxygen would then be due to respired carbon, and then we can infer changes in the biological pump from those oxygen changes. But what we now show, and other papers have shown this also, that there is in fact significant undersaturation or disequilibrium in oxygen. And this is just a figure of surface ocean observations, and the top, the two maps. And here we express oxygen set in percent of saturation. So the orange is slight oversaturation and the blue is slight undersaturation. And you can see that particularly in the high latitudes and in the Eastern Equatorial Pacific, there is undersaturation. And if you look at the zonally average data, particularly here around Antarctica, which is important for our talk here, there's undersaturation of between 10 and 20%. So there is considerable undersaturation. By the way, the blue curve here is the observations and the red is the model. So the model more or less reproduces the observations relatively well. But the important thing is here that there is undersaturation, particularly around Antarctica in the winter. Also notice the paucity of the data in winter around Antarctica. So there's a lot of uncertainty still from modern observations. But nevertheless, the existing data indicate significant undersaturation there. And so what we then do in the model, we can separate the two processes. So the biological pump here, which is so the sinking of organic matter, and then the respiration of organic matter consumes oxygen, and that is what we call O2 soft. So that that represents the biological pump. But in the deep ocean, some of that oxygen is also influenced by the surface. So this preformed oxygen here. So the total is the preformed plus the O2 soft from the biological pump contributions. And the preformed we can further separate into an equilibrium component plus a disequilibrium, and the disequilibrium we further decompose into a physical disequilibrium and into a biological disequilibrium. And these two, essentially, we run the model with and without biology to distinguish between those two, to separate those two. Okay, so and if we look at the pre-industrial control simulation, so this is the total oxygen inventory in the model. By the way, I should say the model distribution of modern oxygen compares quite well with observations. So we think this is a reliable representation of the modern ocean. So the total oxygen concentration here, which is something like 250 or so petamole, is significantly below what we would expect from just saturation equilibrium, which is the purple line here. And the reason for that is that the biological pump here, that's the green, significantly reduces that oxygen in the deeper ocean. But there's also a smaller but still significant effect from the disequilibrium, and in particular from the biological disequilibrium, whereas the physical disequilibrium seems to be really small. So this is for the for the pre-industrial control. And we can also look at the globally averaged horizontal profiles, where, if we start with the equilibrium, so the saturation concentration, that would actually increase from the surface down because the deeper waters are colder than the surface. So at saturation, the deep ocean would have more oxygen than the surface, but the actual oxygen concentrations are of course lower in the deeper ocean. And that is because this biological pump contribution here removes oxygen. And that removal is it's largest in the upper ocean, around maybe a kilometer or so. But you can see here the biological disequilibrium is small at the surface, but it increases towards the depth. And here just a zonally averaged distribution of the biological pump contribution in the Atlantic that shows the lowering of oxygen here in the tropics, in the upper ocean, particularly there. It's but also it's everywhere. It's blue, so this is a negative contribution everywhere. But the biological disequilibrium is also important, and that is shown here in this map for the surface, where you can see negative values, particularly in the marginal seas and around the Southern Ocean. And that signal then penetrates into the deepest layers of the ocean, as illustrated here for the Atlantic. So the disequilibrium is important even for the modern day, even though for the modern it is relatively smaller compared with the biological pump. And I think that may be why many people have disregarded that disequilibrium so far. Okay, so if we move to the Lgm simulations, I don't want to go into all the details here, but just to mention that this is a data constraint model. So we have these three isotope systems in the model, C13, radiocarbon, and N15. And we have the model simulation, the solution of the model has been tuned to fit these data. And we're quite happy with the fit. And that is described in detail in this Muglia et al. 2018 paper, if you're interested. Maybe one important detail here is that the export production global export production is actually slightly smaller in the Lgm, by about 1 petagram carbon per year, already indicating that the biological pump was reduced in the Lgm simulation. So if we look now at the oxygen changes, so on the right, again, the pre-industrial control figure that I showed you before, and now on the left, and on the right, the difference is Lgm minus pre-industrial control. And so for the total oxygen, we see a reduction, which is dominated by this lower oxygen in the deep ocean, as we've seen in this initial graph that I showed. And so this total oxygen reduction is in spite of the increased solubility. So this would be the equilibrium, that would be the solubility component. And in spite of the reduction in the biological pump. And the real reason for this reduction, therefore, and it's dominated by this large reduction in the disequilibrium, in the biological disequilibrium component. So really what we then suggest is that the reduction in the deep ocean oxygen as seen in the data is not due to changes in the biological pump, but rather due to changes in the disequilibrium oxygen. And this is the main message from this paper and this talk. Well, we can look at these different distributions, at the spatial distributions of these different components. And this is again here showing the biological disequilibrium component because it's so important. Here now on the top right, the surface distribution. And you can see a much larger area in the Southern Ocean is in significant disequilibrium. And that influences much more of the deep ocean in the LGM as shown in the lower panel there. And if you look at the global horizontally averaged profiles, you can see the light blue here is the biological disequilibrium component. It really dominates the changes in the total oxygen, particularly in the deep ocean. And some of that is compensated by positive contributions from the biological pump and the equilibrium. So the solubility, the purple line here. Whereas the physical disequilibrium is small and I would say probably negligible in the total. We can also go more into detail and examine the detailed mechanisms for those oxygen component changes. And Samar and Ellen have done that by perturbation experiments where they change only one variable at a time, for example, temperature. So they start, for example, from a pre-industrial condition and then only change temperature. And then we can diagnose all these different components. And in this case, for temperature, you see that the temperature alone would lead to an increase in oxygen concentrations, which is dominated by the solubility. And that, of course, makes sense, right? But if we look at the total, so here's for all of these variables, the changes, again, the biological disequilibrium is the largest driver here. And if we look at what causes that large decrease in the biological disequilibrium, it is mainly sea ice here. And the second largest contribution is from iron fertilization. So both of these are really the drivers, the dominant drivers for the reduction in the oxygen in the disequilibrium component. Okay, this brings me to the conclusions. Well, it's the disequilibrium, stupid. And what I would also conclude is that we should not confuse oxygen and carbon. So please do not use AOU to infer respired carbon. Deep ocean oxygen is significantly impacted by disequilibrium, and that causes a decoupling of the carbon and the oxygen. So for the deep ocean oxygen loss, then we say the reason is the increased disequilibrium. So essentially, we are closing the window, we're closing the ventilation of fresh air from the atmosphere to the deep ocean, which is a different mechanism than the biological pump, which is more, the interior ocean processes and effects of biology. Whereas the disequilibrium is really controlled by the surface conditions. And so different mechanisms control the disequilibrium compared with the biological pump. And we saw that the sea ice is the dominant cause for the deoxygenation, for the disequilibrium changes. And iron is the second most important. And this is really different from the disequilibrium changes for carbon that we've published in the Kadiwala et al. Paper, where we saw that temperature, for example, dominates the differences in the Lgm minus pre-industrial, whereas sea ice was not important. So, there's important differences between the disequilibrium for carbon and for oxygen, and therefore, please do not use oxygen if you want to infer carbon changes. And particularly for cases like the Lgm, where you have large changes in disequilibrium that can be anticipated. So thanks a lot for your attention.
Thanks, Andreas. That was very interesting. A couple of questions before we head into our break. Please use the raise hand feature. Keith Lindsay.
Hi, Andreas. That was a great talk.
Thank you.
To me, it highlights the interesting things you can do with the model that are hard, the separations of terms that are hard to do in observations. I'm wondering if the oxygen isotopes, are you doing isotopes of dissolved oxygen or just seawater?
No, the isotopes we have in the model are C13, so carbon isotopes, C13, radiocarbon, and nitrogen isotopes.
Okay.
And so I didn't mention that, but that's in the Muglia paper essentially. So the nitrogen isotopes are important to constrain iron fertilization, which affects the biological pump in the Southern Ocean. And so we do have more biological pump activity in the Southern Ocean due to increased iron fertilization. We use 10 times the soluble iron input there. But the global biological pump and export production is reduced in the LGM.
Okay, I guess what I was getting at is, this is perhaps then a speculative question. If you had isotopes of dissolved oxygen, then presumably the effects for different oxygen isotopes that you are decomposing, the decompositions would be different for different isotopes. And I wonder if that leads to a way of constraining this decomposition with observations.
I'm not sure about oxygen isotopes. I don't know which oxygen isotopes you would use and how. I don't know anything about how dissolved oxygen, the isotopes of that. But definitely what I can say for carbon is definitely there's differences in the disequilibrium for carbon and for carbon-13, and that has been known for a long time, and that is also related to the different equilibrium timescales. So for C13, for example, it's even longer than for carbon, whereas for carbon it is 1 year. For C13, it is something like 10 years. So C13 is even more in disequilibrium at the surface than carbon. And so I would expect that isotopes can be, can have very much different disequilibria at the surface. But I don't know anything about oxygen isotopes. Sorry.
Okay, yeah. Carbon sounds like that might be useful, yeah. Thank you.
Any other questions posed live?
I do have a follow-up question to Keith's question. So I was wondering, can you use the delta C13 values to quantify the apparent oxygen utilization? And if you know that term, that may be helpful then to better determine the other terms. I mean, solubility is well constrained, of course, and so the delta C13, the solubility component of delta C13 is also well constrained.
Well, as I just said, the C13 has even larger disequilibrium component than carbon, and so the issue with C13 is, well, the large disequilibrium component, and therefore I don't think that it is straightforward to use that to infer AOU or to use that to infer respired carbon. Yeah, well, I think, what you really want to do in the model and what you can do, what we're also planning to do is a decomposition, just like we did for oxygen and for carbon for C13. And then you can kind of compare these different gases.
Yeah, okay, thank you.
Thanks.
Okay, if there are no further questions, we could take our break and return at 11, I believe, yes, for 3 more presentations. Thank you speakers for a great set, and hope to see everyone back at 11. Chat will continue to receive whatever comments you may have. And I'll see you all back here at 11. Thanks.
Esther, do you want to let me introduce now the speakers after the break? You need to unmute.
Yes, that would be great, Arnie.
Okay, good. I continue. And then for tomorrow, you want to start the first session, or should I start with the first session?
I could start tomorrow.
And then I take the second one. Okay.
Yeah. Although, yeah, I'll start and after the break, I'll introduce you and then we can switch. How's that?
Okay, good. Fine.
Yeah. Okay, I'll stop my share in about a minute.
Okay, welcome back to the afternoon, the second morning session. The first talk is by Dylan Amaya, RC coupling shapes in North America hydroclimate respond to Lgm ice sheets.
Awesome, thank you. I'm going to go ahead and share my screen. There it is.
Yeah, I see it, thank you.
Okay, do you see presenter view or full screen?
I see currently presenter view.
Okay. Okay.
Yes, full
I guess
screen,
I just won't have my notes.
Yep.
Okay, no worries. Okay. Hi, everybody. Thanks for tuning in. My name's Dylan Amaya. I'm a postdoc at the University of Colorado working with Chris Karnauskas. I'd like to acknowledge my other co-authors on this work, Alan Seltzer, who is a research scientist at HUI, as I said, Chris at UCU Boulder, Juan Laura at Yale, Sally Zhang, who is a new postdoc or a new scientist at the University of Maryland, and Pedro Denizio, also at CU Boulder. So today we're thinking about hydroclimate during the last glacial maximum. And I probably don't need to remind all of you, but it was significantly different than it is in modern day. But just sort of to set the stage of what we see in the western part of North America in modern day, we have a very wet Pacific Northwest and a very dry, relatively dry United States Southwest. And during the LGM, we think that this was completely reversed, that California experienced much more rainfall, and as a result, it supported large megafauna like these ground sloths that we see here in this artist rendition of what it used to be. And this interpretation is supported by models and proxy reconstructions. So this is from a nice paper from Osser et al. In 2015. And basically what they're showing here is on the right side, you can see different kinds of proxy estimations of what the hydroclimate was throughout the American West. Basically showing that in the American Southwest, blue indicating wetter conditions, proxies pretty much universally indicate that the Southwest was much wetter, whereas proxies, although a lot fewer proxies in the Pacific Northwest, they're indicating generally drier conditions. So sort of this north-south dipole in precipitation regimes. And if you turn to coupled climate models, the PMIT3 archive shows a very similar result. If you include the full physics of the LGM, you can see that there is a north-south dipole in many of these models that pretty strongly coincides with the proxy record. So we think that this is a pretty robust response, but the question is why, right? What physically happened during the LGM to lead to this response? And sort of the leading theory for decades was that well, this had everything to do with the height of the Laurentide and Karelian ice sheets. The fact that the ice sheet sitting over Canada was 3 kilometers tall, about 3 kilometers tall. This would steer sort of the mid-tropospheric atmospheric flow and really the North Pacific jet and push it southward, deflecting storms that would otherwise in modern day hit the Pacific Northwest, but now they're hitting sort of the American Southwest. And really these conclusions were made based on modeling experiments that were primarily just AGCMs, because we just didn't have the computational power at the time to run simulations to equilibrium with an ocean and with air-sea coupling. But now we've made some progress in that arena. We have better computing power, and we can do these sort of longer simulations, and we can also do these interesting single forcing runs. This is from a more recent paper by Roberts et al. In 2019, where they show that it's not just the topography of the ice sheet, but also the albedo of the ice sheet that can have a significant impact on the North Pacific atmospheric circulation. And in this case, they're showing summertime stationary waves and sort of the different stationary wave responses you get in response to LGM albedo versus LGM topography of the ice sheets themselves. So what we're after today are, can we separate the mechanically versus thermodynamic influences of the ice sheets on North American hydroclimate? And really to answer that question, we're thinking about those two impacts on the North Pacific jet and then downstream rainfall. And sort of a secondary question is, what is the role of air-sea interactions and or ocean dynamics in modulating that response? Because now that we do have those capabilities to isolate sort of the ocean impact, that's an important question worth asking as well. So the way we're going to do this is by using a series of CSM1 experiments. These were originally run by Pedro Denizio et al. So I would refer you to their paper in Science Advances if you want more details in the on the model configuration. But basically, we have a pre-industrial control simulation. I'm showing you the surface height for each of these simulations, as well as a measure of albedo, so the top of the atmosphere upward shortwave. And basically just look at North America here, right? So in the control simulation, we have a low land surface that's dark. In the full LGM simulation, we have a high land surface that's really bright. Obviously, the LGM is going to have other boundary conditions set to PMIT3 levels, so orbital forcing, greenhouse gases, everything else. And then we have a series of single forcing runs that we're referring to as a Green Mountain experiment and a White Mountain experiment, where in the Green Mountain, we have a tall ice sheet that's dark. So the land surface has been set back to pre-industrial levels. So this is isolating the mechanical forcing of the ice sheet. And then we have a White Mountain that is tall and bright. So this is isolating the mechanical and thermodynamic forcing of the ice sheet, but setting all other boundary conditions back to pre-industrial levels. So greenhouse gases and orbital forcing are pre-industrial in the White Mountain, which is the major difference between the full LGM and the White Mountain experiments. We're also running these simulations across a range of ocean model configurations. So we have an AGCM only setup, which is being forced at the boundary by pre-industrial SSTs. We also have a slab ocean model setup, which has just sort of air-sea interactions without the influence of ocean dynamics, which is found primarily in the dynamical ocean model run, which will account for advection, Ekman transport, these sorts of things, vertical mixing. And so comparison across the ocean configuration schemes will let us know the relative importance of air-sea interactions versus dynamical ocean changes, or just pure atmospheric driven internal variability, or intrinsic atmospheric variability, I should say. And I'll mention that all of these runs were appropriately spun up. So in every case, the models are in radiative equilibrium with the top of the atmosphere energy budget. So what's the answer here? So in the full LGM run, we're looking at the LGM minus control zonal wind anomalies at 500 millibars, and the P-E response here. So browns being dry and greens being moist. Basically, you'll see that these are very much in line with the PMIP3 archive. You get a southward shift in the climatological position of the jet stream, which is marked by the black contours here. And this turns into a north-south dipole for the precipitation response. So why is this? Well, we can start with the most basic case. The most basic case is a Green Mountain in an AGCM setup. So we just add a bump on top of Canada, and we see what happens in an AGCM setup. And we see that, well, you get a very similar response. You get a southward shift in the jet and a general north-south dipole in the hydroclimate response. And really, this is what a lot of people saw several decades ago in the 80s and 90s when they were doing these experiments with AGCMs. They saw this, and it would not be a stretch to conclude that mechanical forcing is all you need to explain what's going on in the LGM case. And you can see that this response extends throughout the atmosphere. This is a zonal cross-section of the zonal wind over the North Pacific. And basically, you can see that there's this southward shift of the jet pretty much at all levels below about 200 millibars. And we're marking sort of the top of the ice sheet in the purple line, and this GIF is just showing you the height of the ice sheet relative to the wind response in the North Pacific here. So you can just see how high the ice sheet actually was. It reached to about 700 millibars. But what's interesting is that these older experiments that completely relied on AGCMs, they missed some pretty critical dynamics here. For example, if you include an ocean in this response, and I'm sorry, I should mention that in the Green Mountain experiment, again, we're interpreting this as purely mechanically forced shift of the jet stream because there is no albedo effect from the ice sheets. But anyway, as you couple this to an ocean, you get a completely different response. In the atmospheric circulation, you get just a general decrease in the westerlies. But if you look at the hydroclimate response, you get basically the opposite response in the hydroclimate when you couple it to an ocean. So there's some really critical air-sea interactions that are being completely missed in some of these early interpretations of what's going on here. So why is this? I don't have a ton of time to go into the exact details. I'll send you a preprint of the paper if you're interested, but what we think is happening here is it's related to the SST response in the North Pacific. So in the LGM full experiment, we're getting sort of this sort of PDO-like pattern of sea surface temperature response with a cooling and the Kuroshio extension. But in the Green Mountain experiment, we get a warming in the subpolar North Pacific, and that's primarily due to a decrease in the westerlies that you can see here. So as you decrease the westerlies, you reduce evaporative cooling at the surface, and you're giving sort of a positive latent heat flux into the ocean to warm the ocean here. And this is decreasing the meridional temperature gradient. So the winds need to be in thermal wind balance with this. So this would lead to a deceleration of the jet and a very much opposite response. So let's add complexity. We're going to jump to the White Mountain case here. And basically what you need to take away from here is that the White Mountain looks basically exactly the same as the LGM experiment. So this is implying a couple of things. We know that the White Mountain has the same ice sheet configuration as the LGM. So we know albedo is important for the real world or the estimated real world response in the LGM case. We also see that the ocean response is important in sort of reaching the same magnitude as the LGM case, and that the dynamical ocean response isn't that different from the slab. So ocean adjustment processes like the gyre circulation response or AMOC, for example, don't seem to have a strong control on the overall atmospheric circulation response, at least in the North Pacific. And you'll notice that all three of these look very similar across the ocean configurations, but we can compare, excuse me, we can compare back to the Green Mountain, and you'll see that the White Mountain and Green Mountain look basically the same, and that's because they have the same topographical height of the ice sheet. This is basically just saying that in the White Mountain AGCM case, it's completely driven by mechanical forcing from the ice sheet. Albedo has no bearing on this response. Whereas in the dynamic or in the ocean cases, you're seeing the benefit of both thermodynamically driven air-sea interactions and the response of the atmosphere to those air-sea interactions, giving you a response that is much more, which is much similar to what we see in the LGM case, the full LGM case. So why do we think this is happening? Well, we can look at the SST response in the White Mountain case, and you can see it looks very much like the LGM full case. The cooling response is a little bit less because we're missing boundary condition changes like lower greenhouse gases or changes in the orbital forcing, but the ice sheets themselves are driving about half the SST cooling that we see in the North Pacific. And a very fair point here is that this is a coupled response, right? The winds are going to be in equilibrium with the SST, particularly in the winter where air-sea coupling is really, really strong. So how do we sort of parse out the causality, the response of the ice sheets in the atmosphere, and the atmosphere sort of imprinting itself on the SST before it responds back to the SST here. So to address that, we can look at the summertime response. Because if we think thermodynamics are important, the thermodynamic response is going to be much stronger in the summertime when albedo is mattering more, basically. And so basically what we see here is that in the White Mountain case, these are the summer stationary wave responses with shading showing sort of the lower atmosphere circulation response. You can see that there's a cyclonic circulation response in all three ocean configurations. And basically what this means is that the atmosphere is really insensitive to the presence of an ocean in the summertime. And because the atmosphere doesn't care whether the ocean exists in the summertime, then that suggests that the ocean is largely uncoupled from the atmosphere in the summertime, it's true of modern day as well, that the summertime atmosphere cares a lot less about what the ocean has to say. And so we can look at the summertime as sort of an indicator of when ice sheet forcing would first imprint itself on the ocean before it couples back to the atmosphere in the wintertime, where we would get these sort of hydroclimate responses as well. So to do that, we can look at a heat budget, excuse me. We can do a mixed layer temperature budget to see what's driving the SST anomalies, particularly in the summer. And again, I don't have time to go into all the details, but I'll just sort of jump to the punchline here. And it's primarily related to clouds. So this is the SST anomaly implied by changes in shortwave radiation and the annual mean. And this is in the White Mountain dynamical ocean run. The results are very consistent with the slab ocean. Basically what you can see is that the clouds, so that this is the total shortwave, the shortwave related to the clouds, and clear sky shortwave. The clouds are driving a sea surface temperature cooling that's very similar in pattern and magnitude to the overall cooling. But again, this is a coupled situation. The cooler SSTs are obviously going to lead to more low clouds, which in this case, these changes are dominated by changes in low clouds. So we need to be able to see this same response in the AGCM run, where the AGCM has no coupled ocean. And so basically what we're seeing is the same sort of cooling implied by changes in cloud cover in the AGCM run, even without the presence of an ocean, which is really interesting. That's saying that the direct response to the ice sheet in the summertime is to reduce cloud cover, increase cloud cover in this region and reduce SSTs. So if we average low clouds in this box in both the dynamical ocean and in the AGCM run, and we can look at the seasonal cycle of that, you can see that low clouds have increased basically everywhere or in every month in the dynamical ocean run, but mostly in the summertime in the AGCM run. And the differences between these two are showing you the strength of the coupled feedbacks. This is showing you the strength of low cloud SST feedback going from the AGCM run to the dynamical ocean run. But this is showing you that the direct atmospheric response to the ice sheets in the summertime is to increase low clouds and decrease SSTs, even in the AGCM run. So why is this? Why do we get an increase in low clouds? Well, in the summertime, as I mentioned, there's that low level cyclonic circulation that's in the response to the albedo of the ice sheet, basically. And what this is doing is advecting cold air in the western part of the North Pacific, which is increasing inversion strength. And so that's marked by this pink here, making it more stable in the lower atmosphere, making it easier for these low clouds to form. And then the eastern North Pacific, you're getting increased moisture transport coming from the tropics. So increasing moisture in the low levels is also conducive for clouds. So this is happening both in the dynamical ocean model, the SLAB, and in the AGCM, all in the summertime. So I want to leave some time for questions. So I'm just going to jump straight to the summary here, which is represented by this schematic illustration. So this is sort of a comprehensive schematic summary of the atmospheric response in the North Pacific to a tall, bright ice sheet. And so basically what's happening is in the summertime, you are reflecting shortwave radiation because it's a tall, bright ice sheet. This is creating a low-level cyclonic circulation in the North Pacific that's affecting cold air in the west and increasing moisture transport in the east. This leads to increased low cloud cover which is decreasing SSTs in the summertime North Pacific because of cloud radiative forcing. Air-sea coupled feedbacks will amplify this signal. It'll reinforce it, creating persistent SST anomalies that last into the wintertime, where the atmosphere will couple back, or the SSTs will couple back to the atmosphere and accelerate the jet stream because of thermal wind balance, basically, or the winds will be in balance with the SSTs because of thermal wind, and driving a southward shift in the jet stream. So takeaway point here is that it's not just mechanical forcing. You need to think about thermodynamic forcing from the ice sheet, and in particular, air-sea interactions are really driving this response. And ice sheets aren't really all that important, really. It's this SST pattern that is driving the overall southward shift of the jet stream. So this has some pretty clear implications for future climate change as well, in that we don't need an ice sheet to drive a significant shift in West Coast hydroclimate. We really just need a perturbation that generates an SST pattern with the similar size and magnitude. So if you're interested in this work more, I have a preprint on my website. You're welcome to see. This work is under review right now, but I'm happy to take any questions. Thanks.
Thanks, Dylan. Questions? Christine?
Hi, Dylan. That was a great talk. Thank you very much for that. I see that you've got Juan Laura on your author list. So I'm guessing you perhaps have looked at atmospheric rivers in these simulations. So the question is, have you? And the second part to that would be, have you delved into the mechanics or processes with the air-sea interactions in terms of the clouds and the interaction with atmospheric rivers?
The short answer is we haven't looked at atmospheric rivers in these simulations, but we've definitely thought about it, mostly because these simulations don't have daily output. They're only a monthly timescales, but we do have a proposal in the pipeline that is under review right now to look at atmospheric rivers in these sorts of simulations. And so, yeah, we would definitely look at all those sorts of questions. It's the effect of albedo and mechanical forcing on atmospheric rivers, the effect of these air-sea interactions and clouds on atmospheric rivers. Those are all super important questions for West Coast hydroclimate, and so definitely something we're thinking about for the future.
Thanks. Yeah, it's always a bummer when you don't have the right output data.
Yeah, but we're hoping to rerun everything with daily output so we can look at ARs.
Yeah, or I would actually go for sub-daily, actually, for ARs, but yeah.
Sure, hourly, 6 hourly, I guess.
Yeah. Great, thank you.
Jonathan, you had a question.
Yes. I missed the very beginning, and I was just curious, what resolutions were these being run at?
I believe 1 degree.
1 degree, okay.
The model output was saved at something like 2 degree, but the model was run. This is CAM 5, so it was run at 1 degree.
Yeah. No, I have very similar simulations. I'm working on my paper at the moment too. So it's neat to see your results in this as well. And the ice sheet that you use, is this is Peltier's ice sheet?
Yeah, it's ICE 6G.
Yeah. Okay. Great. Yeah. No, this is very similar to many of the results that I've been getting too. Really cool. Wow.
Excellent. Thank you.
Okay. Thank you. There may be questions on the chat you may want to address. Okay. I want to move on to the next speaker, Nicolas Constantino, the dust cycle in South America, South Atlantic since the last deglaciations. Effects on the atmospheric PCO2.
Okay, thank you very much. So I'd like to start by thanking the organizers, especially Esther Brady, for inviting me to this talk, to this series of talks. And today I'd like to talk to you about a project that is only now starting, the dust cycle in South America, South Atlantic since the Lgm, and effects on atmospheric PCO2. And given the early stages of this project, this talk will be heavy on expressions of hope and desire rather than on actual results. And I think it's a good timing for me to show you what we have in plan. So my name is Nicolas Cosentino. I'm doing my second postdoc with Dr. Fabrice Lambert at the Pontificia Universidad Católica de Chile. And Natalia Opaso is a PhD student of Fabrice, and the three of us, we are involved in this project. We are funded by the Chilean Agency of Science by 2 projects going through 2022. And let me see how I go to the next one here. Okay, and before I lay out the ideas for the plans for this project, I would like to talk to you about where I'm coming from in terms of research and where Fabrice and Natalia are coming from as well. So the last 2 years during my first postdoc, I worked on dust, on monitoring present day dust in South America. And even though the contribution of South America to the global budget of dust emissions is low, we can see that South America, and particularly Patagonia, is the only landmass that crosses the southwesterly wind belt. And so in that regard, there may be some effects of dust that are disproportionately more important coming from South America. Okay, so then in my last postdoc, we had a series of dust monitoring stations throughout South America. And we used passive collectors and high volume dust samplers to measure dust fluxes at the surface, both vertical and horizontal. And we published a series of decadal time series of dust, both in Patagonia and also in the Pampas region, which houses the most extensive, less wind-blown deposits in the Southern Hemisphere. Okay, in turn, Fabrice and Natalia, they've been working on modeling the paleo dust fertilization effect. So what we see here is a figure that was taken from their latest paper in EPSL. So what we can see here is the relative contribution of each high nutrient, low chlorophyll region. And here we have the Southern Ocean, the Atlantic and Indian sector, the Pacific sector, and then the North Pacific and the equatorial waters. And the contribution of each one of these regions to delta PCO2 through the last termination due to dust iron fertilization. And what we see is that the Southern Ocean in the Atlantic and Indian account for 41% of that delta PCO2, and the Southern Pacific 16. So this confirms that the Southern Ocean is a particularly sensitive ocean to dust fertilization. Okay, so the questions that guide our current work are related to what are the emission rates of Southern South American dust sources since the Lgm. Nowadays, I mean, there's a very sparse distribution of measured dust fluxes close to the sources in South America, and models deviate quite a bit between themselves in terms of the magnitude of dust emission from South America. So another thing we need to think about is, okay, so we're gonna obtain records of dust deposition close to the sources in South America, how we're gonna translate that into something that we can feed CESM in terms of dust emissions. So that's another thing to consider. We are also interested in the variability of dust deposition since the Lgm and dust emission as well in South America and South Atlantic. We are trying to design what simulations to run in CESM, and we believe that a transient termination simulation may be too expensive, but rather we may do stable simulations every 2,000 years, every 2,000 years. And so the next question would be if there are any accepted forcings and boundary conditions for simulations between the Lgm and the mid-Holocene. Lastly, we would like to gauge the PCO2 response to South American dust deposition at a millennial scale. And we would like to do that with intermediate complexity models, with biogeochemistry, as well as with the CSM biogeochemistry module. Okay, so this is the layout of the project for the next 3 years. There's a field sampling component to it. So we have Patagonian, we want to sample Patagonian lakes and Patagonian peat bogs, as well as the Pampean less. We want to code an interpolation toolbox for global kriging. So kriging has demonstrated to be a good interpolator when there's a lot of distance dependence, spatial structure. And we then need to spend some time searching data and systematizing the available data in terms of dust deposition, which has grown quite a bit in the last years. So we will be able to obtain interpolated maps, field maps of dust for better resolved time slices since the Lgm. The next step would be to use CSM to model the global dust cycle with an emphasis on South America and Southern Ocean. And based on the fields that we obtained based on observations and on CSM simulations, we want to feed intermediate complexity models with active ocean biogeochemistry and the CSM module as well to simulate atmospheric PCO2 changes due to the effect of fertilization by dust on the oceans. Okay, so we, as I was saying, we have already defined what Pampean, what sites to sample in the Pampean less and the Patagonian and in Patagonia. And without going into much detail, we believe we have enough data to go into the last glacial maximum and in some cases beyond that, and to have a good representation of the Holocene as well. Okay, so we have, based on new data that we acquire for South America and also for available data at the global scale, we have irregularly spaced data sets that we want to interpolate to create interpolated data fields, interpolated fields. And we will first use this map. The idea is first to code a MATLAB interface that allows for anisotropic kriging on a sphere. And the main idea here that will separate us from other toolboxes with similar objectives is that we are going to explicitly calculate the uncertainty due both to the interpolation scheme, but also to individual measurement error. Okay, so we have installed CSM 2.1.3 in NLHPC Lefradu, that's the Chilean supercomputer. And we completed that in September 2020. And during the last 6 months, we have made a lot of work to test the installation. So the typical tests required to verify the machine installation, the internal consistency of CSM, as well as comparing output in Lefradu with output from the same simulations at JM. So we have a good sense that this is a validated installation. So CSM treats dust emissions in terms of the siltation sandblasting process, which in turn depends on known factors such as modeled wind friction velocity, soil moisture, and vegetation. And this is embedded in the land model. Also, in general, what's done is to scale these dust emissions based on soil erodibility parameter that incorporates many of the parameters associated to susceptibility to erosion at each grid cell. And we want to follow Otto Blisnet et al. 2020 to scale this soil erodibility map at a continental level to fit global fields of observations of dust fluxes interpolated from the observations that we will obtain for each time slice of interest. And a third step will be to concentrate on South America and further scale the erodibility map based on the new measurements we obtain. So in terms of CSM simulations that we are planning to, we believe that transient simulations through the last glacial termination may be too expensive for our available resources. So we are rather interested as a first step to work on modeling the last glacial termination in equilibrium for different time slices. And based on the expected resolution of the proxy data collections, we aim at performing 4 extra simulations between mid-Holocene and Lgm. But a main question here is if it's feasible based on the availability of boundary conditions and forcings to have this number of simulations planned. Okay, the next step will be to use these fields of interpolated dust deposition every 3,000 years between 6 and 22 kilo-year BP to feed ocean biogeochemistry models, both intermediate complexity models such as CGNI. And one of the questions that we want to address is the time evolution of CO2 drawdown due to dust fertilization between 22 or during the last glacial termination. So Fabrice Lambert, in their latest paper, they see that there's a pronounced difference between the behavior of CO2 response to dust fertilization. So on the left panel, we have age covering the last termination, but in terms and CO2, atmospheric CO2. And the left panel is for the Atlantic and Indian sectors of the Southern Ocean, while the right panel is for the North Pacific. And so we're trying to compare this dotted black line, which is CO2 as measured. And each one of these curves represents dust deposition, the response of CO2 to dust fertilization based on different models. And we see that while in the Southern Hemisphere, there's a protracted and well-distributed in time response, in the Northern Hemisphere, there is a more abrupt response, which is concentrated on the later stages of the termination. So we want to improve on this exercise using better defined, dust deposition fields for better defined time slices and see if this holds. Okay, so the idea is also to perform sensitivity analysis of CO2 drawdown to dust iron solubility. And one of the questions that we also have is if we are going to use the ocean model by itself with the biogeochemistry turned on, or if we should aim for a fully coupled CSM plus biogeochemistry. And this is going to depend on whether, and this is one of the questions that we have, is if we can follow atmospheric PCO2, or if we can follow that evolution, or if it's prescribed to force the model. Okay, so that's the end of it, basically. I leave you with Patagonia and dust event. And here's my email for contact. And I want to stress that we're very, very interested in collaborating with those who might be interested in our work, especially coming from a geological background. I'm still trying to become a modeler, so please contact us in that case.
Thank you. Are there any questions? Yeah, Keith. Keith, you need to unmute.
Thank you, Arne. Nicholas, this looks like a very interesting project. I just put into the chat a command that will give you a single box atmosphere CO2 reservoir that can be used to get an interactive atmospheric CO2 with CESM.
Great.
So this is addressing the question from your last slide.
Perfect. Thank you very much. Yep.
There are more questions?
Well, actually, I have a question to myself, to you. So I was very interested by Jing Su's talk, and it seems that CAM6 and LGM requires some modifications for it to be a feasible simulation. So one idea that I had while listening to his talk was whether he could help us try to use CAM6 and for an LGM simulation, or if it's warranted that we will have to go to CAM5. But anyway.
Okay. I think for us, this is still an ongoing project. So maybe stay tuned. Maybe we will have newer results later. And another comment is that because you are examining the role of dust on climate, on biogeochemical cycle,
yes.
If you use CAM5, the ice nucleation scheme is kind of prescribed. It only depends on temperature and other environmental variables, not aerosol. So if you apply dust aerosol in your Lgm simulation, you only get the direct radiative effects. That's my understanding. So you will miss one piece of the physical picture here.
Okay. Thank you.
Okay. Are there any more questions? Otherwise, I think we want to move on. I don't see any questions more. Thank you so much for the interesting talk. So the next speaker is then Hanna Zanowski with Pacific for radiocarbon evolution during the deglaciation in sea ice trace.
All right. Well, thank you. I'm happy to be the, I suppose, the last talk of today. So I'll take it away here. So again, like Arnie mentioned, I'll be talking about the Pacific Ocean carbon-14 evolution over the deglaciation in sea ice trace. So just to kind of set the stage for everybody here, when we think about the Pacific Ocean circulation in the modern day, it's kind of a broad best description is just that you have some sort of deep inflow of Antarctic bottom water, if you will, into the deep North Pacific, a return flow of Pacific deep water at some shallower levels, and then of course, North Pacific intermediate water formation at much shallower levels, sort of above 1,000 meters or so. And so that's sort of the general idea of the circulation. Now in the past, we can infer that that circulation was fairly different. So this is just that figure from Matsumoto et al. 2002, which I feel like kind of started a lot of this. Basically, the deep Pacific circulation sort of was was different in the sense that the southward return flow was a lot deeper. So that Pacific, North Pacific deep water and the Pacific deep water in general was a lot deeper. The deep ocean was generally more poorly ventilated. And then you have sort of increased North Pacific intermediate water formation and potentially increased upper ocean ventilation as a result of that. And also largely because of changes in stratification, lower productivity is a possibility as well. So that is kind of described in these two figures in color here. These are from Ray et al. 2020. We can see that modern carbon-14 age in the figure at the top there. So, and this is just a section along the Pacific from GLODAP V2, I think. So overall, you get these really, really old carbon-14 ages at around, 2 or 3 kilometers in the Pacific, so 2,000 years old, especially in the North Pacific. And then there's this reconstruction of that, of carbon-14 age at the Lgm from the same paper. And what you kind of see here is that you have these really, really old carbon-14 ages kind of throughout the very deep parts of the Pacific Ocean as well. Changes in ventilation and productivity again. So red in this figure below in the bottom here is higher at the Lgm. Blue generally means lower. And so these are kind of inferred from DLC13 and carbon-14 for ventilation. And you can kind of again see that same structure. This is now a section going, I think, along about 20 north or so in the Pacific Ocean. So along a line of latitude in this case. And again, sort of these red colors, so higher ventilation sort of above 2,000 meters, and maybe to some degree some lower ventilation below that. But of course, one question we do want to answer, though, is sort of how did this circulation actually evolve in the Pacific Ocean, and what's what are all the different ways in which that could actually happen? So that's kind of where we actually bring in our climate models. But one sort of struggle with sort of ocean models and sort of paleoclimate modeling is they don't often actually include a lot of these isotope tracers that the paleo community actually uses from proxy records, and so. In comes then CI trace. This is just a simulation that actually includes a lot of the isotope tracers within the model so that we can actually make more direct comparisons to what the sediment core community does and what the modeling community does. So this is a 22,000 year simulations from Lgm to present day, so 22K to present day. It's a 3-degree ocean only simulation of the CSM 1.1. It's got 60 vertical levels and active biogeochemistry. Its forcing is heat, freshwater, and momentum fluxes from the fully coupled Trace 21 simulation. And then it has reconstructed atmospheric CO2, carbon-14, and carbon-13. So those are prescribed in this model, obviously, because we don't have an interactive atmosphere. And then the tracers involved, we have carbon isotopes, so carbon-13 and 14, delo-18, water isotopes, protactinium, thorium, and neodymium as well. So all of these tracers within this model have been used kind of extensively to sort of begin to make these kinds of comparisons with this model circulation and then to proxy records. And I'd like to highlight Sifan Gu, who's one of our collaborators, who's actually done a lot of really interesting work in the Atlantic Ocean using some of these tracers within this model. So in these figures on the right here, we just sort of have the prescribed atmospheric carbon-14 record and then the atmospheric CO2 in the navy blue. So you've got a kind of increasing CO2 from the Lgm to present day and then sort of decreasing atmospheric carbon-14. And then below, this is a figure that my intern made for me. I'm very proud of. This is just a figure of what the freshwater forcing kind of looks like in this model. This is just the total sum of the northern hemisphere freshwater forcing and the southern hemisphere freshwater forcing over time. And so I'm not going to go into too much details about the location of these or anything like that, but just to say that you've got all these sort of different freshwater forcings at different periods within this model to kind of simulate some of those abrupt climate changes. So. First off, I'm just going to kind of give you an overview of what happens within these simulations. So the easiest way to kind of look at this is to look at the overall ocean circulation itself. So kind of looking at AMOC, or the Atlantic Meridional Overturning Circulation, and then the globally average deep meridional overturning circulation cell in the southern hemisphere. And so that's kind of give you an idea of your upper and your lower limbs of your circulation. And so kind of this is AMOC is taken as the maximum of that circulation at 25 north, and then my MOC in the south is just the minimum of that circulation, just as a kind of quick reference. And so what you see from this is that you, in these sort of major periods of abrupt change, like HS1 or Heinrich Stadial 1, the bowling alley rod warm period in the Dryas, you get these kind of, again, due to that freshwater forcing in this model, major changes in the AMOC. So when you're shut off, sort of a huge ramping up in the bowling alley rod, and then a kind of decline again in the Eranga Dryas, and then over until present day. And then kind of a similar story in the deep limb of the overturning circulation as well, what actually starts out what is considered strong in this model at least, and then that kind of declines over time overall. So that's kind of give you a sense of what the circulation is doing in this model. And then you can also just very broadly look at the global mean ocean properties as well. And as an oceanographer, I can't tell you how much like this feels like blasphemous to average the entire ocean into one data point, but here I am doing that. So this just basically is trying to show you what the potential temperature, the salinity, and the density in this model are doing over time. And so, of course, the ocean is going to warm and freshen and lighten as a result of that. You can kind of see that from this figure again, from 22 Ka all the way to present day. And then again, a lot of these density changes, just because of the way are really largely driven by salinity, it seems to be in this model. And then kind of if you want to understand how things are changing a little bit more, you know, in a less of an average sense, you can also look at TS diagrams. And this is just an example of all of the model points at 30 degrees north in the Pacific Ocean. And so you've got 22 Ka, these are just some time slices, 11,000 years ago, and then present day. And these points are colored by depth. And kind of what you see overall is this sort of shifting of all of the water in this model to this sort of lighter and potentially fresher stage. So, so like I did tell you, I do actually want to talk about carbon-14 today. So this is a comparison of a similar version. This is not actually CI trace itself, the simulation itself, but it is a version of this model using a CSM1, but it's spun up sort of in more present day. So I think 1700 or so conditions, and then core forced. And this is from Jan et al. 2015, just to kind of give you an idea of what carbon-14 might actually look like. In particular to kind of get at these biases. So the top panel here, these are all going to be sort of zonal means across the basins. You get the Atlantic, Pacific, and Indian Ocean. So the top panel is from Schmittner et al. 2013. Second panel is from GLODAP. And then the bottom two panels are actually the carbon-14 within this model. You've got biotic carbon-14, which is actually coupled to the biogeochemistry model, and then the abiotic carbon-14, which is not. And so for my purposes today, I'm only going to be looking at abiotic carbon-14. And when you compare that then to the sort of GLODAP, in again, that second panel here, you actually do get some pretty good similarities, except of course in the deep North Pacific, where you end up having these sort of carbon-14 values that are something like, you know, a little bit more than 300, minus 300 per mil. So there are pretty strong biases in the Pacific in the modern day circulation. And that does carry over into CI trace. So this is kind of now looking at the carbon-14 and now the carbon-14 age over time. So this is back into the simulation now. So these are all zonal means across these basins, just to kind of give you a sense of what this looks like. And so again, over time, you start at these sort of really high carbon-14 values in the model, then decline over time. And then around present day, especially in the deep North Pacific, you have these values that are still, again, more than minus 300 or less, I suppose, than minus 300 per mil. Larger in magnitude. And so you can again compute an age for that though. So you can kind of start to try and think about ventilation in this model. And so to calculate that age, what we do is we just subtract the contemporary atmospheric carbon-14 value from all of the waters in the ocean within this model. And so then of course, just kind of computing it like carbon-14 age like you normally would from that. And so you're starting again at 22,000 years ago, then 11,000 years ago, and then 0. So at present day, kind of going downward in all of these places. And again, what you see from that, not surprisingly, is that your age is declining over time. And again, that is of course related to your carbon-14 values. Doing the same thing because that's kind of what the atmospheric record is doing. So one of the things we do want to get at, though, of course, again, is ventilation in this model, what is actually happening in the Pacific Ocean. And again, when you kind of look at what carbon-14 is doing, one of the helpful things to do is then to actually compare it to some of the other tracers that we have in this model. So one of the things that we do is we look at ideal age, and ideal age is an age tracer, of course. And so what it is, it's set to 0 at the surface ocean. And anytime the water reaches the surface, it goes back to 0, and then ages at 1 year per year in the interior. And so what ideal age does is it ends up telling a different story potentially about ventilation. And that is that basically the Pacific starts out, for example, being relatively somewhat younger at 22,000 years ago. It's a lot older, especially in the far deep North Pacific at 11,000 years ago. And then at present day, it kind of gets younger again. And so that's that again is telling you somewhat of a different story than what your carbon-14 is. But again, that's because it doesn't have that atmospheric record that's being integrated into it. And so ideal age, though, is going to actually err on the younger side. And that is because, again, it's set at this 0 at the surface of the ocean everywhere. And so it doesn't care if it's under sea ice. It doesn't care basically about any of that. As long as it's at the surface ocean, it's going to be 0. And so in comes then ventilation age, which basically what this tracer does, and this is Jiaxu Zheng, I think, put this in this particular simulation. Ventilation age actually takes into account the fact that in this model, underneath the sea ice, you're not actually really getting true connectivity to the atmosphere. And so ventilation age is ideal age, but it's only set to 0 at the surface if the waters actually come into contact with the atmosphere. So if they're under sea ice, then they actually get do not get reset to 0, and that's kind of based on what the ice fraction is within the model. And so when you look at ventilation age instead, you kind of get this similar story to ideal age, but now your ages overall are looking a lot older. Again, they're still younger than what you would see for carbon-14. Not necessarily expecting them to be exactly the same, but kind of what you see from this is that you kind of start out with like somewhat poor ventilation that gets worse toward 11,000 years ago, and then gets slightly better ventilated toward present day. So there's a lot of interesting stuff wrapped up in this, but then what we want to do is kind of think about what the sort of sediment core community does, which in order to sort of infer ventilation changes, if you will, or circulation changes, they tend to do sort of benthic minus planktonic age. And so in my case, what I'm basically doing is I'm taking the bottom, and so they look at benthic minus planktonic ages, and then they kind of compare those two changes at different time periods. And so you can kind of infer a circulation change or a ventilation change if those two age differences are different. So it's a lot of age differencing here, but you can kind of infer that from that. But there is obviously this issue of surface reservoir age, which is kind of a major thorn in the side for interpreting these types of things. But so this is a figure of what this looks like in the model, where you're taking that bottom carbon-14 age, you're subtracting the surface carbon-14 age from it. And now I'm going from LGM and subtracting the present day from that. And so basically, again, this just shows you that atmospheric record again, which is this, that kind of everywhere within this model at the LGM, the carbon-14 ages were older than at present day. And so it is kind of curious, though, like what drives this pattern then? And that is really just the ocean bathymetry, just because the bottom of the ocean is obviously at different levels depending on where you are. And so in these places where you have this really, really old age, it is largely just because you're tapping in, especially like in the deep Southwest Pacific here, you're tapping into waters that are much, much older to kind of begin with. So you can do the same thing then for ideal age and ventilation age. And so ideal age, again, is going to tell you a slightly different story, which is that basically that at the LGM, because these values are all negative and these two figures are on the same scale, this is obviously not for carbon-14 age. They're going to tell you the same thing, different thing, which is basically that, these waters are perhaps better ventilated at present day. And then you look at ventilation age, though, and now it's saying that these waters are slightly older actually in the LGM versus present day. And then you largely get this in the far south, this effect of sea ice actually. And so ventilation age starts to look a little bit more like the carbon-14 age plots, but again, it is not exactly the same tracer. But one of the things, of course, wrapped up in this is that I wouldn't really necessarily do an LGM minus present day kind of comparison for this, because you can't truly infer what is actually happening to ventilation from carbon-14 in that case. And so I actually like to look at the time series here to kind of get at what changes are actually occurring within this model. So now we're just looking at the averages in these four regions in the Pacific Ocean itself, and these are still that bottom minus top age differences across the Pacific. And so in each location, so the North Pacific, the Eastern Equatorial Pacific, the Southwest Pacific, and then the Ross Sea, we have the carbon-14 age time series, the ideal age time series, and the ventilation age time series. And you can kind of see from all of these in the green and the yellow, which are ideal in the ventilation age, these are all very, very similarly behaved, except that, of course, the ventilation age is older, like you would expect. Now, the carbon-14 age, again, is still doing something quite different, and especially if you look at the North Pacific and the Eastern Equatorial Pacific, they actually look fairly similar, and they look similar to that atmospheric record. And so at the beginning of this, you actually have these really, really old carbon-14 ages, but you're actually having waters that are perhaps younger than at other points within these simulations. And so the question is then, how do you, of course, figure out what is truly a circulation change, and how do you, this is always kind of a question within our communities, how do you kind of tease out circulation changes versus just things that are atmospheric changes? And when you look in the Southwest Pacific, especially in like the Bowling Arrow Rod and the Younger Dryas, for example, which are these last two gray panels here, you do start to see that there are some similar behaviors in the carbon-14, the ideal age and the ventilation age. So you kind of dip and then you kind of increase in these age differences. And the only place where you really do actually see sort of similarities then are places where, you know, things are very clearly tied to ventilation, like in the Ross Sea, where you have your dense water formation. And now the green and the blue lines, which are carbon-14 and ventilation age, are actually quite well aligned. Ideal age basically follows the same behavior. It's just going to be a little bit younger because, again, it doesn't care about the fact that there's sea ice there. So one way to kind of get at these sort of circulation changes truly then is you kind of need to subtract things, if you will, based on these ages, based on where your dense water formation regions are, kind of thinking a lot like Matsumoto 2007, that kind of style of thinking. And so what I've done here is I basically just taken the value of all of these different age tracers in the Southwest Pacific deep western boundary current. So this is not averaged in the exact same region as Southwest Pacific, it's a little bit further in the truly deep ocean where I know there's Antarctic bottom water. And I've subtracted the deep age from the Ross Sea. So this is averaged below about 4 kilometers in the Ross Sea. And when you do that for all of these tracers, now what you get in terms of this sort of this age difference then is basically all of them sort of through HS1 and all of these sort of major periods of abrupt change, you're actually seeing this sort of major increase in the age difference of ages of these waters. Okay, and they're all actually agreeing with each other quite well. And so that is basically telling you that there truly is a circulation change. And so all these waters are slowing down. And if you don't believe me, you can then look at this figure over here, where in black, we have that deep meridional overturning circulation at 50 south, like I showed you in the beginning. And then in purple is the speed of the deep western boundary current in this model in the Southwest Pacific, where we're doing those age calculations. And so from that, you actually see this sort of major decline in that current there. And then, of course, the decline overall in the deep global MOC, sort of, which is actually driving some of these changes. So I'm just going to kind of leave that there. But one of the things I think that I really want to get at is maybe really doing a Matsumoto 2007 style circulation age analysis for this entire ocean model in the deep, where you're thinking about using like phosphate, for example, to get the North Atlantic deep water or Antarctic bottom water fraction, and then sort of correcting the ages, circulation ages based on that. Just because the example that I showed you is relatively simple, because I know for the most part that area in the Southwest Pacific basically should just have bottom water from the Ross Sea. So it's relatively simple to kind of think about it in those terms. And then lastly, just if you are interested in using output from this model, it will be made publicly available sometime this summer on the Earth System Grid. More details coming about that, but we will let everybody know, because I think there's a lot of really cool stuff that you can kind of do here within this model. So thank you.
Thank you. Are there any questions? So I do have a question regarding So the plant work with nutrients. So would you also include then dust changes in the simulation? Are you doing that currently? And so if you're putting in nutrients, are you planning to put also then dust into the model?
I do not know if it has dust in it. I don't think it does, but I can certainly find out. The simulation has already been run and I actually did not run it. So I didn't get to decide the parameters of what in and what went out. I know that it has, the major biogeochemical things like phosphate and all of that. And so to some degree, this would be sort of an it would just be, again, what this model does with the phosphate, and it wouldn't necessarily be, is that super duper comparable truly to what then we might expect the biogeochemistry to have done, all throughout the deglaciation. So there's some caveat in terms of that. But again, I'll find out if it has dust in it.
Any more questions? So everyone gets tired, appears to be. If there are no more questions, I don't see any. Esther, do you have anything to say? Otherwise, we will reconvene then tomorrow, 8:15 Mountain Time, with a virtual coffee and welcome, and then speakers starting at 8:30.
That's right. Yep. We will have our discussion tomorrow after the talk, so I hope people can stay around for that, and then an informal chat following that, where I hope we get to chat a little bit more informally with the participants, kind of like if we were actually meeting together in person. It can be difficult to do with a huge group, but we'll see.
So if you have any discussion items, you probably can send it either to Esther or me. We have come up with a few discussion points, but if you have any, then feel free to send it to us.
Okay.
Okay.
Yeah.
Okay, thank you. And
Thank you.
so speakers,
great talk, everyone.
Yeah, please look into the chat and if there's any questions for the chat. Okay, thank you all speakers, and see you then tomorrow.
Thanks.
Thank you. Bye.
Hi, Esther.
Oh, hey, Todd. I'm trying to save the chat.
Okay, good.
I don't see it. I guess does it show up in your document?
Not sure where it saves.
Sometimes it just pops up.
You save it too, just in case. Oh yeah, it says, just says chat saved.
Yeah, it's not very helpful with file names or anything. You have to kind of.
It's in a nested Zoom folder. How nice.
Oh.
Yeah, in the documents.
Yeah.
For all your Zoom.
Okay. Are we the last people on here? Nope.
Yeah.